This morning we have the first talk by Frank Nielsen from Sony and about generalization of Bregman divergences. Okay.
Thank you very much. So I think we have a good introduction these last 2 days on Bayes and duality, and somehow there's a dash right here that is making the interaction very interesting, and we had good tutorial empty yesterday. And today I would like more to give you some flavor of how we can generalize something that is related to the inner duality, Bregman divergence, and how we can also have a special notion from information geometry that we call Bayes-Duality. So my talk will be about Bregman divergence and some of its generalization, and I will also describe a few algorithms on what I call Bregman manifolds. In information geometry, we have a special name, let's say dually flat space, or differential geometry, we call it Hessian manifolds, but let me call it Bregman manifolds so that it talks more to you maybe. So,
maybe the clicker doesn't work.
Okay.
Sorry, maybe also like being close to the mic, that mic is better before the, but you have to speak on that mic, but you have to be.
Okay. Yeah. So, for the frame,
yeah.
Okay.
Yeah.
So this is the outline of this talk this morning. So first I will introduce Bregman divergence and some of its generalization, especially one with two generators. And I will explain what are some advantages that you gain from those generalizations. Then I will explain the concept of Bayes-Duality. Basically, this is a Fenchel-Young transform that gives you two functions, like the convex conjugate and the gradient map, and they are interconnected. I will explain this interconnection by the concept of Bayes-Duality. I will explain also what information geometry can bring you for understanding computing on those special spaces. So I will describe two algorithms and how to view them from the information geometric lens. And finally, I will explain how we can deform a convex function by preserving convexity. And this will lead us to a family of Bregman divergences. So even if you have one exponential family, you will be able to have infinitely many Bregman divergences. So not only the cumulant function or the log partition function. So just to introduce the topic. So the Bregman divergence was first introduced in operation research for finding a point in a common intersection of convex sets in the 60s, first in Russian and then in English. I think people cite the 67 paper. And unfortunately, Professor Bregman passed away very recently. He was living his life in Ben-Gurion University. And what is a Bregman divergence? So first you take a Hilbert space so that you have some inner product and a norm. And you define the divergence between 2 points or two vectors. Here it will be vector Bregman divergences. So between θ1 and θ2 as this function. Okay. And if you look at how to represent this, you can plot the graph of the convex function, your convex generator f. It is a convex things. So the EP graph will be a convex set. And what you do is you take the tangent line at θ2, and you make the difference of the tangent line at θ2 evaluated at θ1, and you subtract it to f of θ1, right? So it's a gap. Basically, you measure a convexity gap, okay? And because you measure this convexity gap, it's non-negative, and only 0 if the two vectors coincide, okay? So it has been somehow very nice for unifying many different topics, like for example, people doing computational geometry working with Euclidean distance. You can see the square Euclidean distance as a Bregman divergence. People doing information theory with the Kullback-Leiber divergence. It can be also an example of Bregman divergence. And actually, Bregman divergence, you can interpret it as generalized relative entropy in some way, in the sense that you take the difference between the cross entropy minus an entropy introduced by F. And people doing sound processing, they have been using interpolar cytodivergence. It's again a Bregman divergence. This one is also interesting because it's scale independent, and this is related to the power spectrum. So if you take a lambda θ1, lambda θ2, you don't change the value of the divergence, right? So what's even better is that you can find a family of generator, like the beta Bregman generators, and those beta divergences, they give you the three members here, okay? So if you want to learn the divergence, you just need to learn the scalar beta in your application. So you have a very powerful unifying family of divergences.
Yeah, can I say something very briefly?
Yes.
Yeah, I think sometimes people call Bregman divergence, but then sometimes we always call Bregman divergence as KL. But then sometimes when people say KL, they mean like discrete, distribution.
Yes, I will come back to that actually. It's a very important distinction because what you can do when you generalize, you can take a Bregman scalar and make it a pointwise integral, and then you get a functional divergence somehow, right? But so here it's vector. People have been working on matrix Bregman divergence. People have been working on functional Bregman divergence with Frischer derivatives. So there are many kind of types. This is why I said the Hilbert space at first. Okay. And actually, in the original paper of Bregman, it's not only vector. There are also infinite dimensional topics. Okay. So to come back to the formula here, you can also view it purely from standpoint as basically a Taylor reminder of a first order expansion. Okay, so basically I can rewrite f theta 1 as this expansion around theta 2 plus a reminder, and if I choose the exact Lagrange reminder, I can rewrite the reminder as this thing. So here we have the Bayesian and we have sign. I always sign should be in English. I always hesitate, but. So you can rewrite your Bregman divergence as this kind of Malanobis where the positive definite matrix change according to the two vectors, right? And this is good because, for example, if you want to know when it is symmetric, basically you will use this thing, and then theta 1 minus theta 2 will be the same. So basically, to be symmetric, you need to have the Hessian constant. So basically, the only symmetric Bregman divergences are generalized quadratic distances. Okay, so this is a very easy way to make the proof. And they are never metrics, so they are never satisfying the triangle inequality. Okay. So to look back, so now we have this drawing. We can say, okay, how can I generalize? Because this Bregman divergence seems to be very powerful. Is there any way that we can even generalize it or make it more powerful than that? So the thing is that can we design over divergences by measuring different convexity gaps? So you just have this drawing here, you forget about the vertical red line, and you say, okay, I want to design my own divergence, how can I proceed? So there are many, many ways, you can be very creative. For example, what you can do is that instead of measuring the vertical gap, you can do like the total least square, you can measure the orthogonal projection, okay, to the tangent plane. Okay? Because here we have epigraph and tangent hyperplane when we take a convex function. And if we do that, we have, oh yeah, there's this window here. But basically what we have is we have the Bregman divergence, the total Bregman divergence, which will be the Bregman divergence times a conformal factor, what we call a conformal factor. Okay? And the good point is that by doing the orthogonal projection to the tangent hyperplane, we have invariance to rotation, which is useful in application. For example, in medical imaging, this has been proved very useful property. And another thing is that because the conformal factor depends only on one side, it's like you rewrite, if you want to compute a centroid, like a Bregman centroid, for example, we know that it is center of mass for the right side, it will amount to rewrite the points. And the rewriting scheme will make the centroid robust to outliers. You can prove with the influence function that you have more robust clustering by taking the divergence. So the details are in this paper, but basically here what we just did is that we replace this vertical line by the green one. So there's another thing that you can do. So remember that we have the vertical red line, which is our Bregman divergence. Maybe what I can do is I can choose two scalar parameters, alpha and beta, interpolate between my theta 1 and theta 2 according to alpha and beta, take the chord that passes through the 2 points, or the second line, if you want, and then define the gap with f of theta 1. Okay? In that case, I know I have something that is smaller than the Bregman divergence. The good point is that don't use the gradient. Nabla f is not there, right? So I don't need to have a gradient. And of course, I can be very close to the Bregman divergence by choosing alpha and beta close to 0 and 1.
I think if you put point, it will be easier because I don't know where to look.
Oh, okay. So, so here we have our Bregman divergence, okay? I have 2 points between theta 1 and theta 2. I choose alpha and beta between 0 and 1. Then I make interpolation. Okay, I have those 2 points here. I take the second line passing through those 2 points, and I take this difference here. So we know visually that this is x. And by doing that, we don't need to have the slope. We don't need to have nabla f. So it can approximate arbitrarily well the Bregman divergence, but still you don't need a gradient, which can be useful. And of course, when alpha and beta coincide, we will have maybe what we can call the Bregman tangent divergence here. But here we need again the gradient. So basically, we just adjust between the red vertical gap and the blue one, which can be made very small, okay? And different properties. So it has some merits in machine learning. So why was Bregman divergence so popular in machine learning? Is maybe this interaction with the exponential family that we heard a lot, right? So I recall the formula for the relative entropy, the Kullback-Leibler divergence. So this is this integral, p log p over q. And of course, depending on your density, it might be non-trivial to compute in closed form because you have to compute the primitive to make the integral calculation. So what's good is that if you have some special statistical model that we call exponential family, which can be written in a very generic form on the left-hand side, but theoretically, if you reparameterize, it's exactly the same as taking a natural exponential family. So I will not talk about sufficient statistics or things like that because it's theoretically the same. So what happens is that when you take the Kullback-Leibler divergence here, you bypass the integral calculation. You just have the Bregman divergence. Actually, what you have is not the Bregman divergence. You have the reverse Bregman divergence. Okay? So you have this df star. Star is for the reverse. It's for the what I call the reference duality. Okay? So what is reference duality is when you swap the parameter arguments. Okay? And this is making all the calculation easy. And how do we, to come back to Empty's question, how do we go from vector to arbitrary probability density Bregman divergence? We do it pointwise by an integral on a scalar Bregman divergence, right? So then we have different types. It can be vector or it can be density, just by the extension.
What do you mean by bypass the integral?
It's just because here, if you want to compute the integral, but here you don't have the integral anymore, right? So this is
But there should be something else.
yeah. So basically, it's Bregman. So basically, you don't need to compute the derivative, the antiderivative. Okay, you don't need to make the integration, right?
I mean, somehow it should be in f, right? That function f you need to compute.
Yeah, because it's a cumulant function. We will come back later, of course. Yeah. There's no big miracle. It's just another viewpoint that it brings. Right? So how do I enter that topic? I was attending this conference in 2004 with my colleague Richard Nock, with whom I work quite a lot. It was 20 years ago in Florida, the data mining conference. And there was this paper, clustering with Bregman divergences. And I met with the team at that time, so I thought Arindam was here today, but next week. And for me, as I was already in Japan with this kind of information geometry community that I was looking at, I could see that people in machine learning were kind of doing things that could be potentially interesting for information geometry viewpoint, but not calling the same thing, the same object somehow. And it got my interest into that. And this paper, the journal paper that was published the following year in GMLR is really excellent, as MT mentioned. I mean, much stuff into that paper. So, I'm going to talk a bit about generalization and geometry now, and then come back to application, okay? So, first, what we can do is we can take a pair of generators, F1 and F2. And of course, if I take F2, that is smaller than f1, so f1 majorizes f2, I can define this guy here with two generators. Maybe I can call it a dual Bregman divergence. Okay? And it's not really a divergence because if I take the same theta prime prime, a divergence should be zero, but here we see that there is some kind of gap that is non-zero. So this is why you can call it pseudo-divergence somehow. It's a generalization of Bregman divergence because if I take the same generator, I got the same thing, and it's above, it's dominating the Bregman divergence. So what is a good application of that? Right? Is it useful for something? So actually, it's useful if you take exponential family and you truncate the support. If you truncate the support of exponential family, you still have an exponential family. Okay? You fix the truncation support, you get another exponential family. So now you can get infinitely many exponential family by making different truncation. Each density can have its own support defined. Okay? And what we can do is we can compute for two different supports, the Kullback level, and then we will find that it is a dual Bregman divergence. Okay? So this is kind of interesting. Of course, if the supports are not nested because of the KL of P log P over Q, it can be infinite, right? So in order to be finite, because dual Bregman divergence like Bregman divergence are always finite, we need to have a nested condition on the support. And the fact that I told you that F1 was above F2, you just, if you have the nested support, you know that the cumulant function, because it is integral on the support, is larger than 0 or 1, right? So it makes sense somehow. So it's a generalization. Let me give you.
You can also write this irrespective of this somehow, or
irrespective of what?
like, is this only for this covering condition? Because I thought that you can do this in general.
No, because Bregman divergences are always finite. And Kullback library, if you don't have a nested support, it can be infinite, right? Because if you P log P over Q, if Q is 0 and P is non-zero, then you. And this is why people use the Nielsen Shannon in practice for GAN, for example, in machine learning, to avoid this kind of overshooting or numerical instability. Okay, so just to present you one application, for example, I can take zip distribution. So zip distribution, this is this guy here. So it's a discrete distribution, one parameter S, and you normalize by this kind of harmonic power members. Okay. And now I want to make k-means, like Bregman k-means, but I want my prototype to be full support, so that I don't have the problem of infinite, and I can use dual Bregman divergence, right? So if I have infinite support of a zip distribution, this is called the zeta distribution. Okay? And what I can do is I can generalize k-means with a dual Bregman k-means, and I can cluster with the prototypes of my clustering which are full support, but the input have truncated support, right? For example, if you take a book collection that is translated in many languages, like for example the Bible, okay? For each translation you will have a S parameter, okay? And then now you want somehow to know how the languages are close to each other from the viewpoint of word frequency in the translation. Then you can apply such a kind of clustering, and you will have some kind of interpretation. Okay, so this you can have a look. So now I come back to duality, which is a core topic of this workshop. So Thomas gave a very good introduction to the topic, and we saw how those convex conjugates are essentially also in Bayes duality. So I recall the Legendre-Fenchel transform, okay? But we can have bad convex function. Yesterday we didn't really mention the bad convex function, so today I want to have only the nice convex function. So I will say that the nice convex function is a Legendre type. What is a Legendre type convex function? We have two conditions. To have the domain, theta, which is open, topologically open because I took Hilbert space for my parameter space, right? So I have some topology, metric topology in use. And then I want the gradient to diverge when it goes to the boundary. Why do I want to do that? Because I want, when I take the Legendre transform of a nice convex function, to be of the same type. If I don't have this assumption, you can have the convex conjugate that is convex, but the domain can be non-convex. And a non-convex domain is not making a convex function, right? Because if you take the epigraph, you will have all the problems that Thomas showed about the gap there, okay? So if we have a nice convex function, what does that happen? First, we have a gradient map, okay? So we have a new parameterization eta, which is a gradient map of theta. And they are reciprocal to each other according to the conjugation. Second things, we have the same kind of function when you take the transform, and then we have the biconjugation theorem, like the moral biconjugation theorem is that if you apply it twice, then you get the same evolutive transformation. And what is called the Legendre function actually is that you're not obliged to take this optimization here, but you can just, because if you make this condition, you know, like you make the derivative according to theta, you will find that it is for theta equal modular f of theta reciprocal, and you plug it here into the solution, you get this thing. This is what we call the Legendre function somehow. This is why Legendre is important.
People realize that theta is actually lambda and eta is mu in my calculus.
Yeah, we should have a tool to make a rewriting of the notation. We should have a macro package. Yeah.
Maybe people don't see, but it's exactly the dual parameterization of lambda and mu we talked about.
Yes, exactly.
Sorry,
No. So once we have Legendre transformation in convex conjugate, we have what we call the Young inequality, or Fenchel-Young inequality, which is like the potential function on theta 1. The dual potential function in convex conjugate on theta 2 is greater than the inner product. So if you make left-hand side minus right-hand side, it is positive. So it could be a divergence as well, and we call it the Fenchel-Young divergence. Actually, Matthew Blondel studies a scalar case for loss function and call it like that. So now, Legendre transform reverses the majorization property. So I want to show you that we can have a duo Fenchel-Young divergence, which is equivalent of the duo Bregman divergence. It's because if you have F1 that is greater than F2, then you have F1 star that is less than F2 star, right? So this is a reversing property of majorization that is done by the convex duality. And basically, I can write my duo Bregman divergence as a duo Fenchel-Young divergence. So it's everything generalized very softly somehow. By this viewpoint.
Sorry, what just happened there? I think that just went like that.
Sorry?
So I didn't understand the last part, the bottom dual Fenchel-Young divergence.
Oh, okay. It's because here, if I have this property, okay, and if I plug in the formulae of the duo Bregman divergence and I play with convex conjugate, I will end up with equivalent divergence. The difference between the Bregman divergence and the Fenchel-Young divergence is the Fenchel-Young divergence, you use the mixed parameterization.
Sorry, maybe I don't understand what is dual. Like, I understand Fenchel-Young divergence, but what is dual Fenchel-Young divergence? Dual.
Okay, this is a good question. Dual because it has two generators, but here I use the primal.
Oh, you mean that's F and F star, and this one is F1 and F1 F2 star?
Yes, dual, not dual.
Dual.
Yeah, en pair. Yeah.
Something I got a bit lost on when working on the Fenchel-Young and the dual is that now we're taking inner products between the primal space and the dual space.
Yeah, so it's in geometry it will be basically what we take now is a natural pairing between a tangent and cotangent vector. But I will not go into the details. But geometrically speaking, you have, if you really want to have a neat understanding, you have to understand the geometric way. I will try to explain a bit without too much details today. Maybe we can talk offline. But this is exactly that. I should maybe put parentheses instead of bracket because it's a different kind of things, right? But we have a dual basis when we have a vector space, like a tangent space, but we have also the reciprocal basis, right? And this is the reciprocal. Actually, here it's a reciprocal parameterization. Yeah. People who do differential geometry, they don't do it like that because they have no coordinate system. They want to be coordinate free. So basically, they put a lot of stuff at the beginning that is difficult to understand, but they are coordinate free in the way that they write it, right? Okay, maybe the most interesting point today for you will be the concept of Bayes-Duality and Bregman manifold. So I will go. So what we think when we apply the Legendre-Fenchel transformation is that we get a convex conjugate, F star, right? But actually we get a bonus, we get a gradient map. So we get two functions. We get F star and we get nabla F, right? And, or nabla F star if you want. And the gradient map or inverse gradient map is related to the convex conjugate. But they have two different meanings. One is that, you remember I told you that there is a reference duality when you swap the parameter order. This is a purple asterisk, okay? And this is in form of this is an involution. But we have also the representation duality. Between what and what do we compute the dissimilarity? Do I compute in theta natural parameter space? Do I compute in moment space? So it depends on the representation. And eta actually is theta star, which is used by the gradient map here, right? So in information geometry, everything is clear because this Bayes-Duality is coupled, and we have a more general way to look at the problem. It's called monotonic embeddings and dual monotonic embeddings. So there's a generalization of that thing. So understanding the Bayes-Duality make it a nice way to generalize for divergence between the probability densities in a more abstract way. So here my Fenchel-Young divergence, if I take the reference duality, I swap the parameter like that, and here I will get let me see something because here I use a convex conjugate and here I take the dual representation. Okay, this will work. So it links the two concepts of reference and representation, which is important.
I think we need more time for this.
Yeah.
So like reference duality, when you write D star, you mean D of F star, right? Is that what the pink star is?
Actually, what I mean is I view it purely geometrically. There's no
generator.
Yeah. I mean, there are, but this is like a function of the manifold. Not, you know, I don't think, I think of F, but as a function, as a potential function in the manifold that can be explicited as F theta u theta chat.
Okay. And then theta star is somehow the gradient of F. So
Yes.
F is there.
Yes.
And then you're saying theta star star maps back to theta. But
yeah, well, basically, the Legendre transform is making this thing relationship between the two dualities.
yeah, I'm trying to. So I mean, I don't need to understand all the details, but I'm just trying to understand what you're saying here. So it's Bayes-Duality interaction. So you're switching stars somehow from the divergence to, you're also switching arguments, and then you're putting the star inside F.
Yes,
Okay.
there are many dualities. I think information geometry is a science of duality somehow. And if you have a good duality, I think what's interesting is to geometrize it. I think you will have clear explanation once I go into the geometric Bregman manifold aspect.
I just want to understand the word bi-dual. So
It's because
bi-dual meaning you're using F star, and then also somehow theta star, something swapped.
yeah, bi-dual is because there's a relationship between the two dualities.
Okay.
You know, like if you take the Euclidean distance, what is the Euclidean distance? You take Cartesian coordinates, you have the formula, right? Square root of the square differences. But if you take any monotone function h, you have hx minus hy square and sum of square root of that, right? So you have infinitely many possible ways to express the Euclidean distance. It is self-dual, it is a Bregman divergence somehow. So I will call it dually flat divergence later once we have the geometric viewpoint. Okay? So this is it. Actually, this is it. So if I have a convex function that is defined on parameter space, I can view my domain, my domain theta with a function f as a manifold. Okay, and in that manifold, I can look at what we call geodesic. And what is a geodesic in differential geometry? Is the notion of being straight. And straightness in differential geometry is according to what we call a connection. And when we have a convex function, because we have they come in pairs, with Legendre type they come in pairs, we have f and f star, each convex function defines a connection that is a lambda or lambda star, right? This is according to f or f star. So I will have a primal geodesic, which is a way to interpolate in red. I will have a dual geodesic, which is induced by the f star. And if in information geometry, the duality means that if I take the half connection between the two connections, I will get the metric connection that we call the day3 interconnection, which is related to the Hessian of f. And if you take Hessian of f star of theta, this is the same G, the same metric tensor that expressed in different coordinate systems. So this is what people call that Hessian manifold in differential geometry. And if you look in the coordinate system, what happens is that a connection here, nabla, we say that it is flat. Is the way that we describe the connection is technically it's called the Christopher symbol. Expressed in a affine coordinate system is 0. In that case, the geodesic equation, because this is 0, it becomes just a straight line in the parameterization. So this is why if you look at natural parameter or moment parameter, one geodesic is straight and one is curved, right? But basically, the mental picture that you have is that, okay? And the duality concept in information geometry is that the half, the middle connection, coincides with the metric connection. And the metric, you can express it equivalently with f or f star as the Hessian. Okay?
So what is this middle connection?
This is Levi-Civil, or Fischer-Rao, if you want. For example, let's take multivariate normals, because this is a good statistical model that we use. We have seen many steps. If I write the exponential family, I will have the natural parameters as we saw yesterday. I will have the cumulant function is the natural parameter is a convex function. If I take as mu and sigma, it is not convex. So natural parameterization is making this full parameterization convex. This is very important, right? Here, if I explicit what happens for the two geodesics according to f and f star, I will find and rewrite that into the usual mu sigma parameterization. I will get this kind of interpolation here, right? With a mixture and with the exponential, right? So I will have these things. And these things are, why is it nice? It's because it's in closed form, because it's flat, right? The differential equation is trivial to solve. But the Fischer-Rao geodesic was very complex, and actually it was solved last year by Kobayashi for boundary condition. So this is it. So if I take mu sigma, I have univariate normals mu sigma 1, mu sigma 2. I have basically three geodesics. I have the E exponential geodesic. I have the mixture geodesic, and I have the Fischer-Rao, which is half used by half the connection. Okay. And here I show you the Fischer-Rao geodesic between bivariate normals here, where I choose the endpoints of the geodesic. So this is called solving the differential equation with boundary values. Okay? And of course, to conclude that, what Kobayashi has done is he has explained something that was kind of a recipe where we embed that stuff into dimension 2D plus 1. And there's some concept that is called Riemannian summation, but basically it's a very nice explanation to get the exponent. Basically, to compute this guy, you need to compute just the geodesic for covariance matrices without mean and reproject. So you make 2D plus 1 dimension, you do something very easy in 2D plus 1, like the SPD cone, and then you go back. But geometrically, it has a very neat explanation. The paper is not easy to read.
So the previous one was just an example. The slides before. Sorry, I'm still. I know you're excited about this, but I'm still stuck at the previous one.
This one?
The previous slide.
Okay.
So here,
I'm taking one F here, and I say, okay, what is the dually flat space of that F?
Yes, and you're just basically giving an example that. Oh, so this is just an example of all of those.
How I instantiate for this special F, what will be the two dual geodesics.
Okay.
Okay.
And I think I more or less see Okay, so the red one is somehow convex combination in natural parameter space, and then the blue one is in the
mixture coordinate or moment coordinate,
the
and then you
dual.
reparameterize by mu sigma, which is your usual interpretation, right?
Okay, and then there's Fisher-Rho geodesic, it's in between.
Yes, but this one is difficult to calculate because you
Why
need,
is that? Like, what's
it's because it's when we say dually flat space, we say there are two coupled connections that are flat, but the Riemannian metric connection is not flat. So the Fisher-Rho or the Riemannian geodesic, the metric connection is not flat, and then you have to solve this equation.
to solve that
But
thing?
here it is zero, then it is
It's easier.
it's just a line segment, right?
Okay,
So
I get it. Thank you.
yeah, welcome.
Sorry, I just have one question. So, because you are talking about this Bregman divergence, which is based on the convex notion of like convexity, right? And then here you actually, the way you present it, you actually use like choose like specific coordinate system. I'm just not so sure the convexity, the notion of convexity actually depends on the.
Yes, you're right. You're absolutely right. Convexity depends on the parameterization. This is why I said that if you take f, this guy, where is it?
Because it's kind of like the.
If I take this guy and I express in mu sigma, it is not convex in mu sigma. But in the dual parameterization of exponential family, it is convex. The cumulant function is convex. So basically, if you take an affine transform, then it preserves convexity. But if it's not affine, it doesn't preserve convexity, right?
I see. So actually, it's not like in some sense like pure geometrical.
It's pure geometry, but it will be very technical to explain. There's something that we call affine Legendre invariance. Basically, the function f and f star, there are two potential functions, which are geometric functions. But if you reparameterize one, because they are coupled with Legendre, it reparameterizes the other one, in a sense that the connection with the Fenshaw-Young divergence becomes invariant. I can show you, the formulae are not trivial. Yeah. But this is why this Bregman divergence, I could call it divergence of nabla nabla star, or dual Bregman divergence, I call it d of nabla star nabla, if I want to be pure geometric, and I can be pure geometric. And actually people call it contrast function because they take a product manifold, and then it's just divergence is a function on the product manifold. Because you don't have two parameters, you have only one parameter on the product manifold.
One question about that slide with the two geodesics being average. So
no, the geodesics are not average. The connection are average. Yeah.
Sorry. So if I remember right, the Fisher-Rho metric is the one that's like locally a KL divergence, right? Like it's like just an epsilon.
Yes.
So what I thought was interesting is that in this case we're only looking at multivariate normals, but the average connection is more general than the.
Yes, here I just have a convex function. I don't think about Fisher-Rho. I call it Fisher-Rho because I think for people, for the statistical model, we used to call it Fisher-Rho, but it's a Riemannian geodesic. It's a metric geodesic. It's a Levi-Civita geodesic induced by the Hessian of f or the Hessian of f star. It's the same metric.
I was just wondering if so that means that basically the average connection is somehow not unique. I can have multiple different f's that could give rise to the same average connection.
Yes. Actually, you have a family of connections called the alpha connection, and it takes the cubic tensor. But I don't want to go into this today. But yes, actually, any affine combination of affine connection is an affine connection. Okay. So, duality in information geometry is to say that this connection is a connection that is induced by the metric tensor, which we call the Levi-Civita connection. So here, if you do, you don't have G here, right? But if I do nabla star half, I found something that is induced by G. So they are coupled with the metric. You can say that they are G conjugates somehow, okay? So, the construction that I mentioned is for any convex function. If we take an exponential family, which is our common statistical model, we have two kind of ways to look at the normalization. One is by the cumulant function, f, as we did yesterday and 2 days ago. Another one is we can just take the partition function. The partition function is log convex, okay, because they are related, right? You will have z equal exponential of f, right? And actually it's log convex, and the log convex function is convex. So we have two convex functions when you take an exponential family, and the question is that what is the Bregman divergence corresponding to for Bz? Z is a partition function, right? So
what do you mean by log convex functions are convex?
I will explain in the last part if you allow me, because I will have a more general viewpoint. Okay. Basically, log convex means that if you take the log of a function f, it's ordinary convex. Okay. So I have the two functions for an exponential family: the cumulant and partition, f and z. Okay. I can define two Bregman divergences because it is convex. So I have bz and b log z, for example. Okay. And those Bregman divergences, I can recover it as special divergence, which we call the Nielsen divergence, which are just this kind of things, right? So the usual thing is that if you have the KL, you have the Bregman divergence on the swap parameters. And if here I take the convex gap not in the extreme case, but as in between the graph here, I don't want to go into detail too much here, I will have something that is called the Bhattacharya divergence, which is related to Rényi alpha divergence, right? So my question is that now I don't take f, I take z. What happens? If I take z, then I will have the fact that I recover the alpha divergences, but not for normalized density, but for positive measures. For example, for the -1 + 1 alpha divergence, and we have the generalized Kullback-Leibler divergence where I have this extra term here, plus Q minus P. And the tilde means that they are not normalized densities. Okay, so basically, if you have two non-normalized exponential family and you take Kullback-Leibler with this formula, you get BZ instead of EF. Okay. So now, I just want to take 5 or 10 minutes very quickly to see that is information geometry just a viewpoint, or can it really be helpful to inspire you to get something more general when you think about problems? I want to take 2 examples. One is that information geometry, basically, either you're a differential geometer and you are interested in dualistic structure in differential geometry, or you are a statistician and you are interested into the geometry of the statistical model, right? And the statistical model that is often used is the exponential family, but we can take over statistical model, like for example, I can take the Cauchy or T-student models, or I can take what we call a mixture model. It's not like a Gaussian mixture in the sense that you fix the components. For example, if I take the probability simplex, I can express it as an exponential family, or I can express it like that, and this is the mixture viewpoint of the probability simplex, the categorical distribution, if you want. And here, if I take the neg entropy, as you said yesterday, this is a convex function, and we can build a Bregman divergence, and we can build a Bregman manifold. Okay. Now, if I'm interested to compute the Nielsen-Shannon centroid, so what is the Nielsen-Shannon things? Is this divergence? It's a symmetrization of Kullback-Leibler where you take the mid distribution. Okay. But if you take the mid distribution of a categorical distribution or a mixture distribution in general, you stay in the same family. Okay, you average your theta parameterization. So you remain consistent. And because we have the neg entropy which is convex, we have a Bregman divergence. And basically, this means that the Nielsen-Shannon divergence will be related to the F. So for example here, the way, if I take sample space alphabet of 3 letters, I can view any distribution, discrete distribution with 3 letters as a point in a standard simplex that is inclined in R3, right? But because they are coupled, the sum should be equal to 1, it's just 2 degree of freedom, right? And this is the natural parameter of our mixture family, if you want. And here we will have prior geodesic, dual geodesic, and maybe Fisher, or Fisher in that case, if you want. Okay. And you have an animation here. What happens is that when the points, the 2 points, passes through one of the vertex simplex, all the geodesics coincide. So you have a special phenomena that happens also in that simplex when you move the distribution. Okay. So I want to compute the Jensen channel between two categorical distributions. What it happens to is the Jensen divergence here. Okay. So basically the Jensen channel when you have the KF symmetrization with the mid distribution happens to be this guy where you have the mid parameter of the distribution and the neg entropy. Okay. So this means that if I want to compute the Jensen channel centroid and minimize the Jensen channel between my centroid P and the input point Pi, I will end up with this rewriting. And then if I remove all the fixed term, I will have this minimization problem, and it's the difference between the convex function and the concave function, or difference between two convex functions. So you apply the convex concave procedure or the DCA algorithm. So you have one way to compute it. Actually, if you like to call new families, if you take the Jensen Bregman divergence, you can say, okay, it's like the Jensen channel, but instead of taking KL, I take a Bregman divergence channel. Okay? I make the symmetrization of Bregman divergence by the same scheme as the Jensen channel symmetrization. Then I end up with Jensen divergence. Okay? So it's two representation, and it has also been called Bayesian. So basically what we have is you have a general principle that if you have a mixture family, then you will be able to compute the Jensen-Bregman centroid. This is useful. So for example, why is it useful? Because Jensen channel is bounded by log 2. But KL is not bounded, it can go to infinity, right? If you have some beams that are very close to 0, then you can overshoot and be very numerically unstable, right? So one way to symmetrize is to have this Jeffreys divergence, which is you had both sides, KLPQ plus KLQP. And the other way is the Jensen channel. There are many ways to symmetrize KL. Here we have two images. I take the histograms. I add a very small amount of noise just to have non-zero beam, because I want to be on my open domain. I don't want to be on the border of my 255 dimensional simplex, right? And I compute this Jensen channel centroid and the Jeffreys centroid, and I compare. So in black, you will have the Jensen channel, and in gray, you will have the Jensen. And if you place the bad guys by putting SM to 0, you can show that the Jeffreys is very unstable. Okay? And this is the input image, which are the two histograms here.
Sorry, where do I see the fact? So I see the gray and black are same. I see the black and gray are the same place, right? But
so basically, when it's non-empty, when the beams are kind of far from 0, they will behave good. Okay. But when it goes very close to 0, they can be very different. And if I put, Jensen channel, you can have different support. It will be bounded by log 2. So even if I don't have the same support, histogram with 0 beams for some color, for example, it will work, right?
And what is the blue and the red line?
It's an input image where I take the histogram of the input image.
Black one is the okay.
Okay. So it's in dimension 255, and I represent it as a histogram here. So this is another way to symmetrize, we will see. It's called Chernoff information, and it has been used a lot in information fusion and in Bayesian hypothesis testing. I just want to give the definition, not to tell you why people thought about that. So basically, you have an optimization problem, you have a max of something that depends on alpha, and this is called the Bhattacharya affinity coefficient, or the Hellinger integral for the alpha, if you prefer. And if you take the minus log, because this is between 0 and 1, you get something that is positive or 0, this is called the Bhattacharya. And if you scale the Bhattacharya, you have something that is called the Rayleigh alpha divergence. So those kind of people are all together by scaling factors. And I want to compute this guy. I don't want to explain why it's important to compute this guy. We will maybe have a look later. if you take the book of information theory by Cover and Thomas, you have this figure here where they show basically to get the good, the best alpha or lambda. Here it's lambda. Here you have a neat interpretation. If you take the categorical distribution and an exponential family, you will have an exponential arc. You will have some kind of bisector, and here you will have what we call the channel of points. So this is a figure from the textbook. But we can generalize it into any exponential family, not only categorical distribution. And in that case, it will be E geodesic with an bisector. Okay. And so, and this symmetrization somehow, it amounts to find the minimum enclosing Bregman ball. If you cast it into a Bregman divergence optimization problem, this intersection point is the minimum enclosing Bregman ball for 2 points. And you can have the Bregman balls for many points. Okay. So I don't want to go too far into the explanation, because just to give you a flavor that there are many symmetrization beyond the Jeffreys and Jensen-Shannon divergence. So what I said here, in those 2 examples, the first example for Jensen-Shannon, I consider the categorical distribution as mixture. In the second example for channel of information, I consider it as exponential family. So I can have this dual view of the same statistical model of categorical distribution, and it gives me some insight on how to make geometric calculation. Okay? And actually, if I have P and Q that are not exponential family, arbitrary density, like for example, GMM, okay? You have 2 GMM, P and Q. What you can do is you can make the geometric mixture of arbitrary densities, and this is an exponential family of order 1. You have only 1 parameter, so alpha, that will go from P to Q. And if you write this guy here, actually, this is an exponential family. This is this exponential family here. And we Grunwald call them log ratio exponential family, because if you expand the geometric mixture here, alpha is your natural parameter, log P over Q is your sufficient statistic only, and then you have the log normalization here. And the normalization is minus the beta area. And because we know it's convex, here it's concave, so there's a unique thing. So it shows you that the channel of information is uniquely defined too. Or it shows you the information geometry that the intersection of a primal geodesic with a dual bisector is unique. So basically, by looking at different viewpoints, you can harmonize the results.
So somehow, so what happened to X is that X is not there in that. So it's with respect to alpha, it's a distribution.
The parameter is alpha here.
Yes. The parameter is alpha.
Yeah.
And what happens to X?
X is a sample space.
So X is observed or no? Sorry.
No, it's not observed. It's an exponential family.
Alpha is the parameter, and
Yeah.
X is still the random variable.
Yeah. And here you have the additional carrier measure that we call Kx sometimes, right? It's one of the endpoints.
Okay.
So basically, what I want to say is that if you have any 2 densities, you can make an exponential family with 1 parameter linking the 2 densities.
Okay.
So you're not obliged to have a Gaussian, V-chart, or you have infinitely many, because you take any 2 smooth densities, you can make an arc, a geometric mixture arc, and this is an exponential family.
You do the same with a cumulative distribution function instead of the density, because then you wouldn't need the real normalization, because the product, the mixture of the CDFs would be normalized. Then the normalized constant, we don't need to bother about the normalizing constant.
Yeah, but here the beautifulness is that the normalization coefficient gives us a lot of information. But I agree with you. Actually, what is very funny also is that the moment generating function, which is dependent on X sample space, is also a convex function. So you can have information geometry of that. It's not a natural parameter space. So you can have dually flatness of sample space with dually flatness of parameter space. And what is the interaction, I don't know. But basically, you have many hidden convex functions somehow. For the CDF, I need to think. I cannot answer now.
You can do it for like 3 distribution or 5.
Yeah. So basically, you can be non-parametric. You can navigate in infinite dimensional. in information geometry, there's this concept of affine manifold. So basically, this is where the representation that I mentioned in Nabla-F and so forth. Even if you are infinite dimensional, you can make a finite dimensional affine space, and then you are exponential family.
Maybe this is useful in. I mean, I think we have in direct distribution or something similar things, but I don't know how that connects with this. This might be useful in model merging.
Yes, information fusion, yeah.
Oh yes, okay.
This is why it's related to Chernoff, but.
Okay, let's talk about it.
So basically, this is what happens. Is that when I measure a distance, I want to maximize, and here I have my Q function, which is convex. They are negative of each other. So this is a Chernoff exponent. You can find it in two ways, even by looking at a function family or solving the optimization, convex optimization problem at first, right? So, and this is a non-parametric view of what's happening, and you have an intersection of an exponential arc with a non-parametric mixture geodesic. I just want to jump to the final part, which is short, but which I think is interesting because it makes the connection with all the things. Okay, so this is ordinary convexity, right? This is a function f is convex if it satisfies that, and the domain is convex. Now what I can do is that I can take t1/2, and here I have arithmetic mean on x, and here I have arithmetic mean on f. Now I can replace the arithmetic mean by two means, m and n. And I will say that the function z is mn convex if it satisfies this inequality, which is a generalization of the Nielsen midpoint inequality. Okay? So we recover ordinary convexity, and we have the log convexity, which is AG for geometric things. This is what your question first. What is log convex? So now we have a good theorem that if I take quasi-arithmetic mean, which is one way to generalize the mean with a monotone function, h, then for example the power means you can have this family, then you know that the function z is m rho, m tau, or rho tau convex if the function t composite z composite rho minus 1 is ordinary convex. So this is why I said that geometric log convex function is somehow log convex because I use t and one is log and one is identity, right? So this is very well done. People have been doing it for 50 years, I think. So now I can make definition. Let's say I want to measure a vertical gap, but not with respect to arithmetic means, but to my two families of weighted means. I can do it like that. And the same way that I get Bregman divergence from Nielsen divergence by making the limit cases, I can have the limit cases of that guy and define mn Bregman divergence. This is just a definition. Okay? There's nothing mystery here. Now, if you make the calculation, you make the Taylor expansion and you make the analysis of that, you get this expression here. And this expression, you can rewrite it as a conformal factor times another Bregman divergence, ordinary Bregman divergence, but on different kind of parameters, you have a row embedding. So this is why I wanted to show you that by duality, because we have this duality that is coming up here. So remember I told you that exponential family, we have a cumulative function and a partition function. They are both convex. Two Bregman divergences correspond to KL and correspond to extending KL. So now I can play with two power means and make a smooth transition between the partition and the cumulative. Okay? And we are going to deform the cumulative function until we reach the partition function. And for each deformation that stays convex, we have a Bregman divergence and a Bregman manifold. So we have one way to unify the two viewpoints that I mentioned at the beginning. This is the last slide. So we are with Alexander Sun here. We are making a library, and end of summer we plan to release it in Python. So then you will have this as a tutorial somehow to make the concepts. So this is all the Bregman stuff I mentioned in this talk, how they are related to each other. You don't have to look at that. And I want to thank my collaborators and to tell you also that there's a special journal that looks into the geometric viewpoint of those aspects. Thank you.
Yeah, thanks. You're learning from Shui from Seoul. Are you supposed to use this one?
Sure, yeah, thank you. Hello everyone, my name is Jonghyun Choi, and I'm here to talk about my work on practical setups and a method for continual learning. So this talk is a little bit off from the Bayes or duality. I don't have anything about the Bayes, I don't have anything about duality, and also a little bit, I'm afraid of doing this kind of talk because this is a little bit insulting to you because I have an infinitely small number of equations compared to any other talk on this workshop, meaning that I have 0 equations in this slide. So compared to the standard learning, the continual learning is usually uses kind of sequence of data coming into the model. So the joint training or standard training, which we usually use as machine learning techniques, just allow to observe all the data at one step and see just all data and update the model parameter, and that's it. And if you see any new data, you have to retrain from the scratch with all the previous data. Okay, so it's pretty inefficient to maintain the knowledge in the model that is trained. Whereas the continual learning, we are just looking at the data in sequence. So when you see some data in sequence, you have to train the model, and when you see the next batch of data, then you have to update with the model parameter, and you forget the previous data and use the new data to update the parameters. And when you see the data in batch, then we call it offline continual learning. So you're allowed to train the model in multiple epochs with the batch of training data. Whereas the online continual learning, you're looking at the data in a stream, and you're not usually allowed to look at the data more than one time. So that's like more constrained setup than the offline continual learning and the joint training or the standard learning techniques. So in this nice, beautiful survey paper about continual learning, they are categorized as continual learning method. And continual learnings in this paper refer to the class incremental learning, where you're looking at the data in different classes in a different time. So this continual learning method can be categorized into 3 categories. The first one is the replay method, second one is regular addition method, and the last one is the parameter isolation one. The replay-based method is allowing to store some of the previous task data, and then you can reuse or replay when you're looking at the new data and then update the parameters. The first subcategory of the replay method is the rehearsal-based method, where you're storing the actual data in the previous task and then replay that when you're looking at the new data. But the pseudo-rehearsal task is allowing you to learn a model to generate the previous data, whereas you're not storing the previous data explicitly, but you're implicitly storing these data with the models so that you can replay this previous data when you're training with the new data. And the constrained replay-based method is storing some of the metadata, like the gradient of the previous samples information towards with the previous model that is trained, so that you can use this gradient information to train the model with the new data. So that is the replay-based method. And this regularization method is using some of the handcrafted regularization when you're learning the model with the new data. And that is called the prior focused. And whereas the data focused regularization method is storing the previous model's information, or the parameters itself, then uses some of the information such as logic information from the previous model's output for the new data, and then regularize your model to train with the new data. That is the regularization-based method. The parameter isolation method is you're fixing the network size so that you can learn the new network with the new data, and you have the parameter with the previous network with the previous data, and merge somehow when you finish the learning with the new data. And that is called the fixed network, so that you're not increasing the size of the model as the task going on. And the dynamic architecture is allowing you to have more models per new task, so that you can get large set of large number of models for each of the tasks. So the parameter isolation task, the method is essentially prevents the forgetting of or the catastrophic forgetting of the neural network, because you're not updating the model with the new data, but it is having the problem of increasing the size of the storage cost for the new model to be stored.
Can I ask a question?
Sure, yeah.
I find this very troubling actually, sometimes the use of the words. So, because for me, everything is regularization.
Sure, everything is regularization actually, yeah.
So
But by their language, it is regularization.
it could be like parameter regularization.
Exactly.
Or it could be data regularization.
Exactly.
It could be memory regularization, right? So then when we start to publish methods where we say, oh, we're going to regularize things with our posterior distribution of the past, then yeah, people say, oh, you fit in that little yellow box. But it doesn't make any sense to me.
It is. So people just say that prior focus methods or the data focus method, rather than they're saying this is a regularization method, because the other data are also playing as the regularization when you're training the new data, right? Yeah, I agree. But by their language, they say this is a regularization method. Right, and this is the trendy setup in continual learning task. This is really popularly used task setup. So when you see these online samples, and they are usually partition them into this sort of task. So this task is having the set of classes well aligned within the time. So when you're seeing this task, the first task, you're looking at the green class, pink class, and the yellow class in the task 1, where I plus 2. And in task I plus 1, you're looking at this blue and gray classes. Task I, you're looking only at this red and purple and blah, blah, blah. So this is the disjoint task setup, where you're looking at this set of disjoint classes partitioned into the task, and you're updating the model. Okay, but when you're looking at these stream of samples, you're not supposed to look at these well-partitioned set of disjoint tasks in training the model, right? So this paper called GDOM is proposing a simple unifying approach for the method to learning a continual learner, where your samples are coming in like in different orders, not they're necessarily disjointly partitioned, but some of the classes can be shared across the task so that you can learn the model in more realistic setup, they say. And in this setup, they say we don't need to worry about like very complicated methods, but we are just having this greedy sampler to sample some of the data in stream into this replay buffer, and you train your model with this replay buffer only from scratch every time you see a new task. Then it outperforms all of these popular methods in different data sets by quite a bit of margin. So you don't need to worry about this complicated methods and math or some loss function. You don't need to worry about it. Just do this very stupid manner of training, and you're getting better results. So that is the message of this GDOM.
So why
Sure.
is that the case? It's because the data changed.
Data change, right?
So the underlying model should be dynamic, and this is what the other models don't account for. Is that correct?
They don't say why it is working in that manner, but they say that they have showcased that this kind of simple method of training the new model with the stream of data, with the sampler, greedy sampler, it just works fine in the engineering perspective. So I think, go ahead.
I mean, I think you mentioned this also on your next slide, like or on the bottom right. And something to keep in mind for this paper is their evaluation is very simplistic in the sense of like what you're looking at is that final accuracy value after doing I don't know how many thousand iterations and so on, right? Like so, there's also the question of like, what does your learner do in between? Like, how fast does it learn? How much does it decay? What's the end performance? And so, like it's doing this, and it's going on data sets that are like very low continual learning data sets in the sense that they're actually kind of very well balanced and sampled, and they're just like sequentializing it artificially. So, like what I'm trying to say is, I think the setup at Ferris is very simplistic. It's like I don't know if this means anything.
I think so.
So when you say you don't think it means anything, you're saying it doesn't mean anything.
I'm trying to be nice, yeah.
But actually, we shouldn't ignore this, right? Even if everything is very simplistic, maybe it's actually suggesting that this kind of regularization could actually be useful, right? So just using data is a regularization that we should.
This is not. Sorry, I mean, like, the thing that bothers me about GDOM is not that it's saying sort of like, if it were that like the ways to select memory in these other methods are poor, and like just taking random samples is fine, I agree with that part. But what they're also saying is that like a naive active learner in the sense of just randomly pick any sample, fill them in a buffer, and train them on from scratch on top of this is better. That's the problem. I don't agree with this, but I don't just continuously retrain your models every time from scratch. I think it's not going to outperform.
It is.
Stuff. It's just like that decision.
So what they are just trying to show is that this kind of from scratch training with the new data is just outperforming than any kind of continuous learning. And that is a simple message that they try to showcase, but they don't actually verify or justify why this method should be the best method for this kind of continuous learners. Right? And it's also very inefficient in terms of computation when you have to retrain from scratch.
Yeah, but these kind of data, are they kind of stationary in the sense, or do they are dynamic, they change all the time?
No. It's like a stationary data set. I think that's the right word. And then
It
you
is.
partition it into like 10 chunks.
That's right.
And pretend it's now continual learning.
Mhm.
Like that's the problem.
Maybe
right?
that's what it is.
And they
you take these endless digits, you just randomly split them into 10 subsets.
different set
And now you
partitions.
introduce them in sequence, and you're like,
Right.
this is continual learning.
Right.
Like, well, is it?
It's just continual word.
It is.
If you see it from a math point of view, I'm sure you can fit. If anybody is not in the kind of context, what you mean by continual learning, because then it's not that you're learning something static. That's boring. You have the world is changing all the time.
Right.
Otherwise, there is no point of continual learning.
Mhm.
It's things and world is static. You learn until you're 10 years old, and then you stop. And then you're fine.
But the message here is that we are supposed to train the model in a really changing distribution, but all the setup that many papers are evaluated on is just on the kind of stationary data, but is having like different partition of the distribution that is kind of fixed. So that is the problem that they try to convince with this simple method, right? Okay, sure. Sorry, can you say that in the mic?
Sorry, I didn't understand that stationary data versus changing distributions. If you have a data set, and even if you are doing random sampling, there is no control on the, like for example, M&S also. If you are taking different parts, still the distribution will change.
It is a little bit changes, but the amount of changes within the static data, when you divide it by the partition, then it's not going to be large enough like you're facing in a real world situation that you really see the big changes in the distribution when you see the stream of data coming in. So that could be the reason, and that is what Martin is saying about the stationarity.
Even if the larger, if like I understand they are not talking about the amount of data, but if we think that whatever very, very, very large set of data, still, do we still say if we are chunking them distributions?
Then that we don't know, right? But I expect that is going to be the larger changes in this very small data sets or partitions when you're doing the continual learning evaluation.
Sure, thank you.
Yeah. Robert, you have a question? No?
I'm getting a mic.
Okay.
Because I don't want her to have it.
Sure. Thank you. All right. So when you're looking at this GDOM paper, then I was thinking that maybe we can do this greedy, we can do better than this greedy sampler because this should be the baseline, right? So we are sticking with this idea of core set problem as we have the same kind of thing in the Thomas's talk in yesterday, right? So the core set problem is not actually well-defined concept, right? This is just the notion of something. Like this is the if you have a subset of the data, then if you have this trained model with the subset of the data and you perform the same as the model with the train with the whole data set, then we call it as core set. But the methods to find the core set is not well defined too. So we try to just diversify the data in the replay buffer, or we try to make as much as close to the core set sampling rather than just the greedy sampling. So we call it rainbow memory by defining a scoring function. Oh, I have an equation here. Sorry. So this is the equation. So I have defined a scoring function to measuring the diversification, or the distance from the. Let me say it in this way. So the stability of the sample to the current model. So when you transform the some sample with some transformation like rotation or hiding the half or whatever, then you're passing through the sample to the model, already trained model, and measure the confidence of that sample's class and see the variance of the confidence. If the variance of confidence is large, then we score it like, yeah, this is the uncertain sample according to the currently trained model. Okay, and if some sample is giving you the same kind of confidence regardless of the transformation, then we call it this is pretty certain sample for the currently trained model. So with this uncertainty as a scoring function, we sample in a class. We sample the data in a class with the uniform steps by the score and consisting the replay buffer by the hope that this is going to be having some diversification. Then we think that we name it as a rainbow kind of LGBT stuff kind of the diversity. And the other thing that I was in mind is when you abbreviate this method as RM, and this is the leader of the BTS, that is a Korean singer, and they call it RM, and so that you can remember it much more easily. And also we try to further diversify the samples by the data augmentation. This is a simple trick that we are using to further diversifying the samples in the replay buffer and also the stream data. So by using these two simple tricks, we have a method that is outperforming the previous methods, including the GDOM in many different data sets, also in different blurry portion. So here, the blurry setup that this GDOM is trying to convince is that rather than this disjoint setup that the class is not going to be shared across the task, this blurry setup has the classes shared across the task. And let's say you have one task, and this task is usually have the class 1 and 2 samples, and the other classes sample, like the samples from the class 3 and 4 and 5, can be appearing with the lower probability than the class 1 and 2. Okay? So the classes that has a higher probability to be sampled is called the major class, and the classes that has a lower probability to be sampled in that task is called the minor task. Okay? So this blurry portion 10 means that you have a 90% chance of sampling from the major classes and the 10% of the sample chance you're sampling from the minor classes. Okay, so blurry 0 means that you have zero chance of sampling from the minor class, which means that it's a disjoint setup. Okay, and the blurry 30 is the popular setup that this GDOM is evaluated on, and across many tasks. Many task setup, our proposed method is showing pretty good performance. Okay, and the problem or the issue that we found in the blurry setup is that it is kind of realistic compared to the disjoint setup that you can see other classes samples in many tasks, but in a forgetting perspective, it is actually easier setup than the disjoint setup because you are allowed to see the samples from the other classes at the beginning, and by the minor class chance you can sample from the other classes. So from task 1, you usually have all of the classes sampled, and it's actually not seeing any new classes introduced in the task progresses. So I think this is also not realistic because in real world, you may see a really the new class at some point, right? And you will see some classes with a low probability to be sampled, or they're arriving at some task time slots. So we make explicit partition of classes to be introduced newly. And the other part should be also shared across the task. So we can say the incremental blurry setup. So say some of the classes should be introduced, meaning that some of the classes having the 0 probability to be sampled, and some of the classes having the minor class probability setup, minor class probability sampled, and some of the classes having the chance of major class sampling probability, so that you are having many mixture of the classes introduced in each of the tasks. And also we found that some of the methods are, all of the continual learning methods are evaluated at the end of the task. So suppose this method, actually this is our methods, are having pretty good accuracy at the end of the task because we are having the big updates at the end of the task. So we are waiting for all the samples coming in the task and we are updating the model at the end of the task. But usually all of the models are evaluated at the end of the task. So you're looking at the average accuracy at all of these task transitions are having this much of accuracy. But in the middle of samples coming up in the stream, but models are not going to be updated. But this continual learner should be evaluated at any time. But this kind of evaluation metric is not really this realistic. So we propose a new methods or new metric to get all of the accuracy summed up under the curve, so that you can evaluate the methods more accurately, so that you're not seeing like artificially high accuracy compared to the actual accuracy that you're looking at any time of usage of the continual learner. So this is a new metric that we are proposing in the paper. Right. And also, this stream of data is supposed to be labeled on the fly by a human annotator, right? So whenever the new samples are coming in, maybe, then the scenario that I was imagining is that one human annotator or the n number of human annotators are label these samples on the fly. But when you're looking at this on the fly labeling scenarios, some of the samples may be wrongly labeled, right? But the continual learning, all of these continual learning methods are evaluated on the assumption that all of these annotations are super correct, which is not really true, right? So we are trying to, go ahead. No?
You look at log loss or something.
Right.
It's fine.
No, if you have wrong label, then it's wrong label.
But like on average, some. Yeah.
But still, if you label a dog with a cat label, then you're looking at a very different data distribution with a wrong label data. So
Okay, maybe we can talk about it.
sure, yeah. So if you have a wrong label data, then it is going to be affecting very bad on the sample models to actually well recognize the well distributed data sets. So that's why this wrong label is adversely affect the model's performance. And we try to enforce this diversity on the wrongly labeled samples, but it's actually worse than the greedy sampler and worse than the random sampling methods. And I was looking at why, and I have an 8-year-old daughter, and at that time I was 6 years old. And I was reading a fairy tale about the ugly duckling. And when I was reading the story, then I found that why this diversity-based sampling method is having a problem. So when you're looking at this ugly duckling story, then all you see about this swan is labeled as a dog, right? Labeled as a duck, right? Then when you try to diversify sample in a replay buffer, then all you supposed to collecting is this wrongly labeled data because they are really diverse from the appearance perspective, right? So that's why all you can add in the replay buffer is just wrongly labeled data. So when you train the model with the wrongly labeled data, then your performance on the clean inference data will be very bad. Right? So that's why.
But you can train by allowing the label to be wrong. Yeah?
What do you mean?
It's like probabilistic formulation that you allow the label to
You
be
let it
wrong.
be. You let it be.
To be probabilistic, allowing the label to be wrong.
Yes.
Yeah. So when you have this wrong label in the data, then your model that is trained on the wrong label is going to be wrong, right? So when you supervise the dog with the cat, then is the model is well recognized as the real dog? No, right?
I thought we were saying the same thing.
Yeah, it could be lost. Unless the dog self-identifies as a cat, then what do you do?
So you have to clean the label. You have to relabel that with the correct.
About that, right? But that is the problem that we are solving.
No,
That-
but you don't need to clean the data. No, this is supposed to be on the fly. Isn't it?
Yeah.
Am I missing something?
If
Maybe I'm missing something
if you
that
have
I
to clean
don't.
the data, then you miss the point.
If I clean the,
setups don't usually allow what you're trying to
it is.
Sorry?
do. These setups don't usually they
They are
constrain themselves to some weird form that they don't allow what you're suggesting. Like I agree with what you're trying to say.
There is no probabilistic
Just like
formulation.
the formulation is like too constrained. It's like standard discriminative neural network thing without anything in there.
So the data is somehow.
It's like
Yeah, but okay, then you have problems.
Well, that's where the problems are.
It is.
Yeah, but all of this is because of that, but
Yes,
anyway,
yes.
maybe we
it's
don't,
very
yeah.
the root.
Sure,
Yeah.
yeah, I hope that is clear, okay? Sure. So with this in mind, then we want to still enforce diversity in the replay buffer to make the continual learner perform well on the new data sets, right? Then we are simply using the partitioning way of looking at the data and see how much the probability of this label should be correct, okay? So by a simple methods of looking at the confidence of a sample with the currently trained model and see if the confidence of the labeled sample is kind of corresponding to the confidence of the currently trained model. So say this is labeled as a dog, and when you inference with the model with this dog class sample and see the dog class confidence is pretty high, then you're kind of saying that, okay, this sample is likely to be correctly labeled. And if the confidence is pretty low, then either the model is not fully trained with the new samples, or the sample is going to be wrong labeled. So we stick with the the latter prior. So that's saying, okay, this sample may be having a wrong label if the confidence of that class is pretty low. So we are partitioning this sample with the high confidence with the correct labeled sample, and with the samples with the mediocre confidence level is called the R partition, which we are supposed to clean up the labels of looking at by using some robust learning technique that is estimating the correct label with the appearance of data. And if the samples with the very low confidence, then we are saying that, okay, this is completely wrong labeled, and we are not having any chance of cleaning this label, then we are just not using the label of this data and use this as a self-supervised manner. So we just get this encoder better with the representation errors. So by just simply partitioning these samples into 3 categories, then we are getting the methods that is outperforming the other continual learners with the label cleanup methods combined on different data set on the different noise set up with the different portion of the labels, different portion of the wrongly labeled samples in the data set. Okay, and currently all of these continual learning methods are evaluated and trained on the explicit boundary existence, but usually the data has no boundary and they're coming into the continuous distributions, right? So the conventional continual learnings are making this discrete task boundaries that has some set of classes into this task, but all we see in the stream of data is just the probability of some of the samples are coming in the stream from the different categories. So what we are just proposing is the boundary-free continual learning setup that where the samples are coming in the probabilistic manner from any classes at any time. So the first probability distribution that we are considering was the Gaussian distribution. So we are saying that some of the samples are coming in the Gaussian manner in time, and we also say that the real world data are often periodic, so we are modeling the periodic scenario of the repetition of the Gaussian distribution over time, so that some of the samples are appearing with a different probability in different time with different peaks. So that is the periodic Gaussian distribution. And the next setup we are thinking of is that, this is the setup that I was thinking at the very beginning of the continual learning, is that we can assume that some of the relationship of the new classes are known with the previous classes. So, in the North Europe, maybe in the Sweden or Iceland, or these countries are having many languages about the snow, they say. So they have like 24 different names of the snow. So they have 24 different categories of the snow. And in Korea, we have like numerous number of kimchis, but all you imagine about kimchi is just one type, right? So when you make a classifier, or when you make a robot and you want to deploy it, or you want to sell it to new countries, then you have more fine-grained description, or the more fine-grained categories of that class in that culture space, right? So in that case, we have to expand your label space by knowing that this label is connected to the previous classes, whether they are the parent class or the subclasses. Okay, so that we are calling the hierarchical label expansion. So for example, if you have a bird, then we are in the next task we are having this some specific bird categories like the limpkin, African gray, I don't know what this bird is, and goldfinch or American fruit or whatever. So with this in mind, then you know that this limpkin and African gray is the sort of bird, but we are having the explicit new categories, so that you can borrow some information from the superclass more specifically to train a model for the subclass expansion at the next task. So this is a new setup that I was imagining, and this is pretty useful that I was thinking. So I just proposed this setup in the previous conference in Paris last October. And specifically, we have these two depth scenarios. The one is the single depth, and the other one is a multi-depth scenario that we have the two-level expansion of the label space as the task going on. So that is the more specific hierarchical expansion scenarios of label relationship. And the next setup that I was thinking that is useful is that the real-world applications of continual learning is the continuously updates problem. So then we are applying this continual learning scenarios to the embodied AI agents, where this agent is going to be predicting the next steps action by taking the visual information as well as the language information about the instruction. Say we are instructing the robot to bring up a bottle of water from kitchen, then this agent is trying to navigate the environment and trying to spot the fridge in the kitchen and opening the kitchen, fridge and bring up the bottle, and then coming back towards the point that the human is waiting for, then the task is success. So that is called the embodied AI agent. So you're going to predict the stepwise actions by looking at the visual information and the instruction that is given. So that is called embodied AI. And in that scenario, we are thinking that when the new task comes, so we are actually defining what the task means for the embodied AI agent. So what we are thinking is maybe a new room or the new environment is a new kinds of information for the embodied AI task. Yeah, so when you train a model or the agents with the bathroom only, then when you want to adapt this agent to the kitchen and the bathroom that is newly seen, then you have to retrain the agent from the scratch. But using the continual learning, you can only update some of the partial parameters or the entire parameters with this limited amount of data using this kitchen and the bathroom information, so that you're having much more efficient manner of training the new environments. Okay. So here we are specifically proposing two setups. One is behavior incremental, so that the agent is learning a new action, or your an agent is going to learn a new environment over time. Say you're previously learning the bedroom and bathroom, and now you're learning about the kitchens as a new label. So here you're having kind of class incremental way of setup for the embodied agents, but it's in different axes of the action space and the environment space. Okay, so we call it continual learning embodied agent. The next setup that this is the last setup that I was thinking that is kind of useful, is that the human labeler or data even for that kind of concept is not always available for updating the model continuously. So for example, if you want to let this new model can recognize or can extend their ability to a new class for the cats and sheep, but oftentimes we don't have any human data, and also we don't have any data collection for this cat data or sheep, but we want to get this new class information to be learned the model in a continuous manner. Sometimes we don't have this, we don't have this data. And this setup is not proposed by us. This setup is proposed by a very recent work by this guy, and they call it name-only continual learning, okay? So without data and without human annotator, we want to learn a new concept, so they call it name-only continual learning. So to tackle this name-only continual learning, we are thinking of, yeah, maybe we can just use this web scraped images or web scraped data by putting this name as a query to the search engine so that we can collect some of the data for that concept and then train the model. So this web scraped image is having a problem of the noisy information, right? So when you search like the dog, then you're getting maybe this is a cat, right? Then you're getting some cat image, but you're also getting some illustration or any kinds of crazy images can be searched through the web engine, right? Then what we are trying to propose is to, instead of getting this web scraped images, we are just getting the generated image. We are generating images by the help of large models of image generation model, right? So that we can generate some of the cat images or the dog images by giving them a prompt to generate these images. But the issues of this naively generating images is limited diversity. When you're trying to generate the images of cat, then all you generate is just these cat images that are looking pretty similar to each other. So to diversify this generated image, we try to get different type of text prompt using the chain of thought or the other kind of techniques. And also we try to diversify further by using the multiple generator combined to get more different set of images to be included in the training sets. So this is the ongoing work, but we haven't finished it, but we will finish it soon. And this is the idea that we are trying to get. All right, so this is the proposed setup that we are thinking of that is useful for the continual learning literature. The continual learning is motivated from the necessity for real-world deployment, but the literature is quite far from the real-world scenarios. And they are always, even today, evaluated on this disjoint class incremental classification setup that is quite problematic. So we have to rethink about to bring the research to the real world by thinking about this setup is really useful or not. Okay? And we are kind of making many number of effort to make this more real world friendly setup for the continual learning literature. I have 20 minutes and I have one more set of slides for the methods of continual learning that we are thinking that is useful for tackling some of these setup that we just proposed. So in continual learning, there are two issues. The online continual learning, there are two issues. One of them is insufficient training for each data in stream because we are not having much of time to train some of the data in stream with many epochs, right? And the other one is the data is always imbalanced at each time step, right? So for some of the classes, we have many samples, and some of the classes are not having sufficient number of samples to train. But in a data set, so-called data set that we are using to train a model with the supervised manner, and the supervised manner is usually having the balanced data for each and every classes. So these two problems is making the online continual learning difficult to make the model fully trained for or to understand the full concept of the class. So to tackle these problems, we are looking at this concept of neural collapse in a balanced distribution. So this neural collapse is a phenomenon that when you're having the balanced data set and you train fully, the well-trained, then the classifier embedding and the sample embedding for that classes are going to be clustered well in a very tight, width of the cluster. So they are gathered together in the embedding space. So that is called the neural collapse. That is known in this paper. And this sufficient training on the balanced training data set is leading to the neural collapse phenomena. And this final structure that is having this neural that has the neural collapse is called simplex equiangular tight frame. And they are having like most of the classifiers are try to pose with the equiangular distances in the high dimensional spaces. So some of the paper, some of the work is trying to induce this neural collapse in the continual learning setup. And in the offline continual learning setup, you have some luxury of the multi-epoch training in a stream of data so that you can induce the neural collapse by introducing the sufficient number of prepared class embedding spaces. So say if you have like 10 classes at the first task, and you don't know how many classes is going to be happening in the data stream. So they just free define, let's say 1000 class classifier, and then they try to make these samples to one of the vacant slots of the classifier embedding to be collapsed to each other so that they can try to induce the neural collapse in the offline continual learning setup. But in the online continual learning setup, we don't have the luxury of having the many iteration of the training. So it's kind of impossible to, it's not impossible, but it's really difficult to make this neural collapse happening in the online continual learning. And also, we think that this predefined number of class embedding is kind of not making sense too much. So what we are trying to do is make the features embedding and the quickly moving closer to the corresponding classifier vector that is not happening yet. So our idea is, before the idea, when this online continual learning without doing anything, then your training error rate, which is kind of a proxy measure of the neural collapse, is not zero, meaning that it's not having the neural collapse yet, because we are only allowing one epoch training of the data in the stream. But when you're doing offline training, then you're achieving the neural collapse pretty easily because you're looking at the data many times in many epochs. So we try to attract these existing attracting the sample to the existing classifier sample. So when there's new sample coming in, like this is the classifier for the dog, and this is a bird, and this is maybe, I don't know, what is this? And when you see a new class sample, maybe this is orange, then this is trying to attract one of the class embedding that is already trained. Let's say this Bayes class for the So when you do this t-SNE visualization, so when there's when there's new sample is coming in the space, then they're kind of attracted to the already well-trained classifier embedding closely. But when you're doing 1000 iteration after one task introduced, then they are having nicely balancedly distributed in the embedding space. So we try to sort of achieve this kind of thing without having much of iterations. That is what we're trying to do. So then the first question that we have is how to move the sample close to the non-yet existing classifier embedding. So we here define an implicit and arbitrary classifier embeddings different from existing classifier embeddings. So we don't know the new class embeddings locations, but all we know is it should be different from the existing class embedding or the existing classifier embeddings. Okay? So such as this. So to achieve this goal, we use this negative transformation thing. That is simply simply using the transformation of the existing data with the very hard transformation, like the rotation extreme, like the other way, we flipped 90 degrees or 180 degrees. So with this hard transformation, we can make this visual image that is very distinct from the existing image, and they are claimed as having pretty different semantic from the existing semantic by the extreme transformations, like the hard rotation of the 90 degrees or 180 degrees. So one example that this hard rotation or the hard transformation is having different semantic is that humans have pretty strong bias of the face recognition. When you're looking at the face upright, then you can recognize this person without any problem. But if you rotate it 180 degrees, then even though you know this person very well, humans also having so hard time to recognize this person because it's upright, it's different. Okay, so this paper is claiming that this negative transformation or the hard transformation is even changing the semantic quite a bit from the existing semantic. So we are using this hard transformation to get different semantics classifier embeddings to be mapped for the newly coming data. So we call this distinctive implicit classifier, but this should be really not enough because this is somewhere not close to the existing classifier. So the newly coming samples are going to be maybe closer to the newly introduced classifier embedding, but it's not enough. They have some residuals, of course, right? So we have some crazy conjecture that there could be a pattern of the residual amount and the sample embedding. So we think that, yeah, maybe looking at the sample embedding, we may get some pattern for the residual amount for this embedding. So we have this crazy conjecture so that we are proposed to learn a mapping, an embedding to a residual by looking at the many embeddings and residual pairs. We are learning some model to get this weighted sum of we just get the mapping from the embedding to the residual so that when you see some samples in the inference time, then you're looking at the embedding and see the residual amount, the expected residual amount, and we correct it by this expected amount of residuals. So what we expect by this proposed method is here. So without doing anything, this color denotes each class samples. This blue samples are going to be clustered closely to the classifier for the the red classes, right? And this green class sample is maybe clustered towards the existing sample because this new classifier for the green class is not going to be trained yet. So they're supposed to be close to any existing classes. But with this distinctive implicit classifier, we are hoping that this green sample is going to be closer than before to the green class classifier embedding, and with these residual corrections, then we are hoping that this sample is going to be much more closer to the classifier embedding that is going to be learned in the later timing data stream. So by using all of these proposals, that we achieve pretty good amount of training error rates. And here the red one is our proposals combination, and here the blue one is doing nothing, and the green one is using enough number of epoch training for the newly coming data. So this proposed method is showing pretty good amount of training error rates so that we can induce pretty good amount of neural collapse. That is not achieved fully, but it's pretty good amount of neural collapse is achieved by these two proposals. And visualizing this effect of the proposed components is here. So when you are having the baseline, meaning that this is the confidence of the class 4 samples. So if we have achieved good neural collapse, then this guy should have really high confidence that is close to the class 4's classifier. So we should have some good confidence value indicated here when you have a good neural collapse. But when you do anything, when you do have nothing in the method, then this class 4 sample is having pretty good confidence in the other classes because they are close to the other class classifier embedding in the feature space like this. Okay, so this is actual observation that we are seeing for the class 4 samples without doing anything. But when you're having this distinctive implicit classifier methods, they are still does not have much of the confidence value increases. But when you're doing the residual correction only, then it's having something. But when you're using all together of this proposed method, then you're seeing this class 4 sample is having pretty good confidence value or the probability output at the class 4 embeddings. So with this result behind, the quantitatively our methods are having pretty good accuracy in the online continual learning setup, either in the disjoint or the Gaussian scheduled continuous stream of data in different number of data sets that is popularly used for the visual classifications. Right, so this is the real take-home message of today's talk. So we really have to think about whether we are going into the right direction for the continual learning or the Bayesian learning or whatever, okay? And instead of improving the state of the art in May, right? So we have to really think about whether the problem that we are trying to solve is the right problem or not by imagining the real world application that this kind of setup is going to be used. And we have proposed some number of setups for making this continual learning more realistic, and also we propose a time efficient online continual learning methods using the notion of neural collapse for the first time for the online continual learning. And we're going to present this work in the next week in Seattle in a conference called CDPR. And also, I want to discuss this thing a little bit. Do we need really the continual learning for the large model? Because the continual learning usually tackles the stability and plasticity dilemma, whether we have to tackle about the forgetting, as well as we have to adapt this model to the new data quickly, right? But if you have the large models, then does the forgetting actually happening or not? And some of the papers are claiming that even the GPT models are having some forgetting, right? But we don't have really the good metric to measure the forgetting yet, and also we don't have a really good metric to measuring the adaptation of a model to the new data. So I have this big challenge question whether this large model that we are popularly used now is having this issue of forgetting or the quick adaptation of the new methods. I don't have a good answer, so I think this is a good question to you guys to think about when you're designing a method or when you think about the problem that you have to solve. Thank you. I finished 5 minutes.
Yeah, thanks a lot for Martin to do this tutorial on continual learning. The original plan that we had actually done is that there were a couple of people coming to work on continual learning. So Martin and Siddharth and Jonghyun and then Razwan and many other folks from Alberta. But some of them agreed that they will be happy to do some tutorial, and then I asked all of them, and
they jumped it on me.
But then they didn't end up being on this day, so Martin is actually filling in for them. So yeah, thanks a lot for spending 1 hour and doing this. And sorry, we are a little bit late.
That's fine. I'll just start.
Martin is a great guy from Germany, and really fun to hang out with. That's the best introduction I can do.
Yeah, I get angry sometimes, and then sometimes. And I try to do nice things. So yeah, I mean, I didn't know what to call this tutorial, and maybe like even tutorial is an overstatement. So like Eugene had called this a conversation, I'll maybe call this an overview instead. And that's just because like continual learning people do a lot of weird things, and it's like there's no like really formal definition and so on. So we'll kind of walk through what the issue is first, and then like how people are trying to attack that from different points of views. And if we have time, I don't know if we'll have that, we can get to this last part on like the road to lifelong learning, basically like things beyond just updating continually, like what else you would do if you have life cycles. But let's see if we get there. I could kind of skip this motivation almost pretty fast because we've heard a continual learning talk just now, But basically, well, there are lots of like really large models right now, right? Like they kind of, if you go on the x-axis and then you see here time, and then you see like number of parameters of these neural networks on like a logarithmic scale, they're kind of exploding and they're just getting ridiculously large. And then people like retrain them a lot. So there were these papers finding like absurd carbon emissions of just one training cycle of like GPT, and then you know, like every company does a new one of these models and they start from scratch again, and like we're just heating the environment, and the question is like, why are we doing this? And I guess part of it is because there's this like idea of how we do this training in these machine learning models, right? So if you look at like Google Cloud ML and what they tell you of like how to do machine learning, one of the interesting quotes there is like, important, like developing a model is a process of experimentation and incremental adjustment, and you should expect to spend a lot of time refining and modifying your model to get the best results. And you can similarly Google like machine learning workflow, and interestingly, you'll find these kind of depictions of errors everywhere on the internet. So it's always going to tell you like, well, there's like these 5 to 7 easy steps of how to do machine learning, and once you've done them, you've solved the problem. So it's like, define your objective, collect some data, clean it, select an algorithm and a model, which right now is basically just like deep neural network SGD, test on some like predefined test set, and you're good to go. Integrate this into your applications, right? Well, yeah, maybe, but the question is like, why don't we instead just adapt machine learning models over time? And some people are doing this and some people are not, and there are some challenges when you try to do this, right? So one of the big challenges I guess that everyone talks about, that I will talk about mainly today, is what has been referred over decades as the sequential learning problem. So I want to answer before I tell you what the sequential learning problem is. This is a good sort of quote to show you basically the empirical side of it, and to answer Jonghyun's question of do we need continual learning in large-scale models. It's showing that both GPT 3.5 and 4 have in the task of identifying prime versus composite numbers, in just the span of 3 months that they've been live, between March 23 and June 23, the accuracy in that specific task has gone from 84% to 51 on like the same test set, right? So the same kind of service, it says here, is behaving very differently at different points in time. And so the question, of course, is why? Well, we don't know the precise answer because we don't know what they're actually doing. But if I had to speculate, it would be that they're just updating their model sequentially on just whatever new data they're feeding in exclusively with like stochastic gradient descent or something. So what we typically do, right, like imagine you had 2 tasks in GPT, like one being prime versus composite numbers, another one being some other mathematical task. If you shuffle all the data, like you typically do it, and you train on it and you measure, like you train, you do like mini batch kind of stuff, and you watch like what the training accuracy is, it looks very nice, right? Like it's gonna learn these tasks eventually in this large model with enough parameters. But if you were to chunk it in 2 blocks, and you have like task 1 and then task 2, and you're doing like mini batch sort of kind of stuff from left to right, there's a long time where you're only going to see data from task 1, and then there's a long time where you're only going to see data from task 2. And given your choice of model being a neural network and like stochastic gradient descent or something, you're going to observe a training accuracy that kind of just mirrors how your data is ordered when you feed it in. So you're going to perform very nicely on this green kind of stuff as long as you keep updating on the green stuff. And once you keep only updating on the purple stuff, it's basically going to swap. If you want to know like that this is exactly opposite of how humans do it, you could read this nice like neuroscience paper by Flesch in 2022. They kind of do experiments where they quite naturally show that humans perform really poorly in the top kind of thing, and actually require that kind of structure over time, like in the bottom one. Is this surprising? Like I actually am kind of confused when deep continual learning papers started coming out. There were people kind of saying like, there is this surprising thing of like forgetting, and I'm like, why is it surprising though? Because if you think about it, like what we're doing is we're doing multiple things. So first of all, we're using like an empirical kind of loss estimate, like a surrogate for the actual risk, right? And then we're summing over the data instances of that mini batch. We're individually evaluating the loss for every point, we're summing it, we're normalizing it, and we're doing a step. So if we do this for like 3 tasks, but we're only doing it for like task 1 in this kind of cartoony depiction of like what a loss landscape would look like, well, you're going to see data from task 1 and you're going to converge to that kind of some nice local minimum, some area that you'd like. And now you are in this blocked kind of scenario. You're going to do like these iterative stochastic gradient descent updates, and you're only going to see data from this like blue kind of task. What's just going to happen is you're just going to start drifting towards whatever kind of solution best describes this data that you're currently seeing. And you just keep going like that. And it's a bit like, it's so simple that this will happen in a lot of like your model choices and your updates if you're doing these like kind of greedy updates on like support vector machines or neural networks, etc. Right? So it's no magic, but somehow it's a thing that people are trying to solve. So in fact, like this is a thing that people have been trying to solve, or people have been talking about for a really long time. So this, 1 second, right? This kind of slide I just had, the paper that people are typically referring to is like catastrophic interference and connectionist neural networks by McCloskey and Cohen in '89. But even if you look at like the notes of like Ray Solomonoff in the like seminar where the term AI was coined, it says like that the particular homeostat has the problem, you probably can't read it, that it has no memory of previous solutions, and like going from A to B takes as much time as then going from B to A again, which is kind of not ideal because you've already seen A, you've already learned it, like why would you sort of forget all about it? You have a question?
Yes, so if I think of on the slide before, and even kind of the slide before, this argument about like kind of this stochastic gradient path, can I think of this as like the sampling for the stochastic gradient is actually not uniform, as in, you know, like it's in the first way you try the training order, it's basically saying my stochastic gradient set is something uniformly for my data set, and the second one is not something uniformly for my data set.
So, yeah, this is an excellent question. So I was showing you the simplified picture, right? Because I'm showing the simplified picture where there are like 2 tasks. You could also think of green and purple as like the same task, but you have some really like hard shift in the data set, right? We've heard about like covariate shift. Like imagine if you do have sort of a thing you want to do, but then like something changes like really, really strongly, you'll also like adapt to the change and forget about whatever the previous thing was, like, right? So if say you have a language model like who's the president, and then suddenly the president changes, like you'll forget who the old president was maybe because you're just overwriting it. But yeah, you could see it like in this kind of view, you could kind of see it like that. Was a second. Yeah. So, okay, so I didn't put a slide on it because I didn't want to talk about like a lot of neuroscience stuff because I'm also not a neuroscientist. But the way I understood the experiments they do is they have these environments where like a tree is placed in a particular environment. It has like certain amounts of leaves and branches and so on. And people can decide whether this is a good tree to sort of thrive in that environment. And then they'll instantly get like a reinforcement learning style signal of like, yes, this was a good or a bad choice. And the way that people will learn what a good choice and what a bad choice is, if they make a bad choice and the thing that's presented afterwards has some correlation with it, right? Like, let's say the leafiness, if you so will, increases, and then you'll again get a signal and they realize, oh, it was because of the leaves changing or something like this. If you keep on just like random examples, then it's really hard to form like the correlations for you as a human, right? That's at least the, again, I'm not the neuroscientist now, the psychologist coming in is like, no, that's not how it is.
Well, it's worth pointing out that it depends on the nature of the material. So if you have items that vary in a lot of features, only one feature is diagnostic, then people do better than the others.
Okay, so I guess it's very nuanced. I shouldn't be making these neuroscience statements. Yeah, thanks for that. All right, so I hope we've at least gotten out of the way that like there's this like sequential learning problem, and it's anything but magic. So when you like read a paper and it's like, oh, there's a surprising thing for getting, it's probably not surprising at all. And so now there are as you've just seen in the previous talks, there are like 3 perspectives before the 3 perspectives. There is another question.
Okay, to the previous slide. But the forgetting thing. Is the learning rate going down? Because implicitly you're assuming that the model is constant. And if you do that, when you have learned, the learning rate should go down.
Yeah,
But if you have a constant learning rate, you essentially implicitly assume that the value of the previous data become less important. So you're actually having kind of a moving window type of thing. Like you're emulating a dynamic model. So then this behavior is actually correct. It is correct for what you do. If you don't want this behavior, you have to change the way you're doing it.
Yeah, we're going to change the way we're doing it.
Yeah, but
Like,
why is that a problem? Because this is what you're asking for this. If the training rate is a constant, this is what you're doing implicitly. And then this is behavior is perfectly what you tell the model to do. And then you kind of...
I mean, there is a trade-off, right? We're going to talk about it in a second. Like you can, like if you lower the learning rate of someone too much, you're going to be very stable. Like you won't be able to learn how to do things. If you actually have a very new task coming in, like how are you going to learn about it?
Yeah, but that's not the problem. The problem is that you assume here, you assume that the model is kind of dynamic because the learning rate is constant.
I should also be making the small disclaimer that like some of the stuff I'm presenting in the tutorial is not necessarily my opinion. I'm kind of presenting the way that like the survey is kind of portrayed, right? Yeah.
No, it's more that if the learning rate is constant, you're implicitly assuming that the model is not constant. The model kind of is dynamic, but you don't encode it dynamic. You encode it dynamic in a way that you're kind of forgetting about the data.
Can we pick this? This is like a really
no,
good
but
point.
It's like you presented something and then you complain, and it's kind of wrong because it's doing exactly what you would like it to do. It's like if you don't want this behavior, we have to change it.
Can we pick this up when we talk about how to change it, and we can discuss this again? I think this would be nice. So if we want to change the behavior, so people are usually looking at this from like 3 perspectives, if you so will. Like it's the thing that Jonghyun was having on his priors, on his slide with like this categorization of the survey paper. I view this like slightly differently, so I have both terms of like what I think this is and what people call this. So this one thing is like this rehearsal perspective that Jonghyun was showing. I think this is just about like looking at this problem from the side of the data, basically. So what I mean by this is that it's very essential, right? Like if you believe that the problem is not in learning rates or something, but you believe the problem is in the fact that you're no longer seeing this green data over time, and you could just like interleave the data. So maybe just continue interleaving it, like build up some memory of the data from previous kind of tasks, right? And so basically have something like a memory buffer. People call this all sorts of different things. Sometimes they call it like experience replay. But essentially, like take some of the data points that you found are most important to the solution of a task and store them in an external buffer if you don't have issues with like privacy or any other kind of concerns of this nature, right? So your model's going to keep training, and you're going to just keep on storing some of the important examples. And so let me just give you a very intuitive example from like 1992 of like what the idea behind this is, right? Like assume you have some source training data which are these like zeros and ones on the left, you have 2 features on x and y axis, and you have a shift in the kind that you see here in like feature 1 where your target training data later, or like a second task or something, is moved to the right? And if your model had learned 4 hyperplanes to separate this, you could now of course say, okay, there are 2 hyperplanes that you can retain, but there are 2 hyperplanes that you can move. And you're going to move them by some kind of update. Now the question is, but how do you also retain the solution of the previous kind of on the source kind of data, right? Like how do you still solve the source kind of thing? And if you go at this from the data perspective, like not thinking about the hyperplanes, you could essentially just select like 3 points, store those, and if you sort of came up with a solution again, you would probably find a decent solution. right? So if you store this like 0, 1, 0 there, you'd get some kind of line that separates them there. Maybe not being the exact kind of line that is drawn there right now, but rather similar, right? So I guess the thing you could talk about here is really this, what we said it's not a, said it's a concept. The concept of corsets. So you could think about, you want to store as little as possible. So what is basically like the smallest weighted, if you so will, summary of like your larger data set, that if you were to train on that data set, you'd find a similar, like within epsilon solution or loss of your original problem, right? So like here, Q is like some kind of model, some kind of hypothesis you're forming, and P is the full data set, and C is this coarse set. You want to be able to be within epsilon of the solution on the full data set. And of course, you'll have to realize that this is very specific to the data, the set of hypotheses or queries, that's what's called Q, and like the model, right? You're choosing, and your cost functions you're choosing, like this is all like the subset you're going to find is very specific to the choices you make. Now, I said I'm not a neuroscientist, but I think like a lot of the continual learning literature is very heavily influenced by insights of like neuroscience, psychology, and cognitive sciences in general. So there's a bit of a caveat that people recently got inspired by quite a lot, which is that in 1997, Robert French and probably a lot of other people said that it's probably really unlikely that like mammals, humans store actual data points over time. Like that does not seem like a very efficient mechanism. So can there be something else that we do that still gives the same sort of idea? And the thing that people sort of hypothesize is happening, which will be on the next slide, is that there might be like a pseudo-reversal mechanism. So rather maybe than replaying the actual data points, you replay sort of some approximation of it. So what could that approximation look like? Well, I guess what this refers to in terms of inspiration would be complementary learning systems theory, where it's hypothesized that there's a replay mechanism between hippocampus and neocortex. So one of these systems will be like a short-term adaptation system to rapidly learn new information. And the other system will be the one to like basically slowly learn, build up, consolidate over time. And so hippocampus would be the system hypothesized to like pick up information fast and then play it back to neocortex to consolidate it with all the things that have been learned in the past. And if you, like I, are a machine learning person, or a deep learning person even, then you'll realize you could probably do something very similar in, in discriminative and generative models, for instance. Like even if your task was sort of just a classification task, you have a very stupid neural network, you could always train a second model that's like some sort of generative model that could replay, so speaking, your past experience to this discriminator to make that interleaving work, right? So you don't memorize samples directly, but you'll just build up a generative model of the data distribution you've seen, and you'll use that to basically understand what you've seen in the past. And you can use like some sort of, you could formulate this in like various different ways. You could replay, and then you could do all sorts of like routing through your network if you so will. You could weight the samples, etc. So that's kind of like the data perspective. We can do like small sorts of breaks in between these perspectives. They're really short. Like I said, I'm trying to get the concepts across. Because obviously, I don't know if MT would say it's the dual view, but the opposite sort of view of this would be to not think about data, but to think about like the optimizer and how to actually learn with this data. So questions so far?
So, is there any way to choose a setup to guarantee that you will have this equation?
I'm not a corset person, so I don't know. So in continual learning, what will typically happen is it kind of goes the other way around. Like you don't think about like what the epsilon is, but rather there's some very strong constraint on like the amount of samples or the memory you have, and that just dictates everything else in a sense, right? Like someone tells you, my device is very small or something, I only can store like 50 samples, and kind of everything else comes from that. I don't know the other way around, like if you don't have sort of like, you say I can store however many samples I want, pick the optimal thing depending on something, I don't know, or maybe someone else knows. Well, I mean, at least not for deep neural networks, that's this one I'm sure. For other models, I guess like there are more proofs for core sets, so I could imagine. We don't know there?
Yeah, this epsilon is mostly for theory. No, it is. Okay, sorry. I was saying this epsilon is mostly for theory. Yeah, that's where it goes.
Okay. There's another one.
Just to be comparing the two, so the argument you give about neuroscience, right? Like obviously the human brain doesn't store examples, but because we don't have the neural kind of real estate to do this, right? But like on computers, it's super cheap to store all the examples. Like I mean, memory or like disk space is very cheap. So like, is there kind of some normative argument here where you think it's actually a bad idea to store examples, or are you just saying like?
Medical people will absolutely despise this solution. They will be like, I have to store an example, you're out. At least the ones that I've sort of talked and worked with. And then with pseudo-rehearsal, like you have a bit of a hard time convincing them because there are all these arguments of like you can still recover things from a generative model, etc. But you're having slightly less of a hard time now. At least you have a fighting chance, and probably it's a bit more reasonable because you can like directly infer the patient or so, right? So I think this is like very, so like this perspective is probably by far like empirically the most successful in quotation perspective that many people use. Like I mean, Jonghyun was talking about this quite a lot. So there's nothing strictly against this. It's just like maybe it's not always applicable in all kinds of situations.
I kind of have the opposite intuition. That you could store everything. Like the number of brain states is greater than the number of atoms in the universe, so you could store everything if you wanted to, but that's not how it works. And when you look at this, you see that like this becomes more expensive, bigger than this data, so there's definitely an incentive to this.
I have a short question. So, I guess in some sense, like the whole, it was briefly discussed before, like the idea of the gradient descent has like this implicit assumption of like IID data, or that like, you know, we're now receiving things in chunks, and then I guess the takeaway I got from the memory setup is basically like, okay, let's make IID data look like IID did in some sense, or it's like the, yeah. Is there like any sort of actual like statistical connection to this? Like, is this any sort of transformation in distributions? Can we think about it this way?
Is there any kind of I mean, it's definitely connected to the optimizer, right? Which is like the thing we're going to talk about next. That's why I kind of said like maybe this is dual in a sense, because one affects the other. Your question is interesting though. I'll have to think about that one. Like writing down like what actually happens when you do these like interleave things with memory examples. I mean, there must be, right? Like the question is just like, what does it look like? Okay, so maybe it's a good time because I guess people are kind of asking for it to look at like this kind of more like optimization view of this. Like, I mean, to some people, I guess the data thing is the most intuitive, especially if you introduce the problem such that you look at it from this data perspective, right? But now there are lots of arguments on like, well, there's an optimizer choice you made and a learning rate, etc. So like, how does that influence this whole thing? And so, what people usually, again, like old ideas, old problems, maybe made up problems, we don't know. But like if you look at the organization of behavior, like HEP in 1949, they call this the stability plasticity or sometimes sensitivity trade-off, which is kind of like what machine learning people think about too, right? So you have this, this is where kind of Razvan comes in implicitly, who should have kind of done this tutorial because he's like on this paper and some other papers that are gonna come now, but he's giving mental support, I'm sure. Anyway, so if you see this cartoon I sketched earlier here again in this picture, right? Like you can think of two kind of things. So first of all, you have one task, you're going to get a solution to this task. This is fine, right? And now you're going to have a second one. And the question is, what are the things you can think about? So one option would be you have a extremely, like, almost infinitesimally low learning rate, and then you would actually probably not move this direction. Like this error that happens is if you actually have a large learning rate and you're just going to go like see the new data and bounce into the second thing. You could look at these, so this is like what's plastic or what's very sensitive. Because all the new data you're seeing, you're updating like with a very large step, so you're moving to that new kind of area here. If you set the, in the worst case, the learning rate to 0, you would not move at all, right? So this would be very stable, but you're not going to encode kind of the solution of the second task. Where you probably actually want to end up is if you were to do joint training of these kind of two tasks, like you actually just take both of the data at once, you shuffle it, you train on it, you'd probably do something like this here in this cartoon, right? So you would end up in some region that's not exactly like the blue point, it's not exactly the red point, but it's somewhere in between, right? So the question basically from the optimization perspective could be, if you first arrived at the red point, how can you make sure that you basically move away from it, but you don't like radically jump with extreme sensitivity just to the blue point, but you get some kind of trade-off in between? I'm not sure this answers your question.
Let me try a new question.
Ah.
Okay, let me try a new one. You're trying to balance two things, you know? These are, why isn't there kind of two models? One is kind of stable, and one is kind of fluctuating, and the fluctuating get predicted by the stable. So one is kind of supposed to have constant learning. This is kind of, you're learning the life skills, and that doesn't change by the weather, you know. But then you have some kind of very adaptive things, and then you get this separated. Of course, you can use the long-term learning to kind of predict the short term, and whatever you get wrong, you can kind of correct with the other model. Putting both in one model, this is not going well.
Yeah, so I am like 200% with exactly what you just said. Like it goes back to like this complementary learning brain thing, right? It's just that somehow, I don't know, machine learning people have this obsession with like one model can rule it all kind of thing, right? You want like one large model to do everything. Maybe that's it. Like, and I'm not sure I'm with you. I'm not sure I agree that's the best way of doing it. But like I guess like this is all you're right. I should say this is on the assumption that you're saying that there needs to be like exactly one model and there cannot be more models than one, right?
No, it's possible to have two thoughts at the same time, and then we swap. You know, it's like yeah. Okay, sorry.
No, that's a good point. Like I kept saying, like disclaimer, I'm not sure I agree with everything, right? Like so, yeah.
So this picture that you draw, right, like similar to the other slide you have, is all in 2D, and so it looks like, you know, there's this one optimum for task one, and if we move away from it, like in this little potential, we get worse, right? But obviously, if we optimize parameters in a million dimensions, like in most of those directions, it's just going to be a flat loss surface, like it's not going to actually get worse. So like in networks, for instance, like if you find these two solutions, like probably there's actually going to be a large kind of collinear space in which like nothing actually gets worse. Like you can just move around and sort of solve those.
Yeah, this is like pretty much what neural network people are gonna try to do now. Yeah, absolutely. I'm not sure they'll necessarily formulate it as such, but basically, yeah, I'll show you like two slides. Basically, this is the intuition behind that a bit, right? I'll have it in a very abstracted form, but good. Yeah. This is more like a joke slide. I just found this very funny. Like we had this in a previous tutorial. Like if you look at like what Plato said, there exists in the mind of man a block of wax, like harder, moister, and having more or less purity in one than the other. The soft are good at learning but apt to forget, and the hard are the reverse. So I don't know, maybe this is like the first mention of stability plasticity. Well, jokes aside, let's get to the part like what people do, right? So yeah, just another version of this cartoon. So a paper that came out, which some people will say is Bayesian, some people will say it's not Bayesian, depends on like how you go about it, is called elastic weight consolidation. It became extremely popular. And it's basically, in this cartoon, what it's saying is like, sure, like don't do this, like if you have your parameters for A, right, like your theta star A, and you want to move to like B, which is this light shade that it looks like, don't do this blue kind of arrow. Don't just naively optimize. But you know you have a neural network. There's a lot of parameters. Give it some penalty, and this is what elastic weight consolidation is going to do. Specifically, I'm skipping the Bayesian parts because I'm not even sure like if it's necessary to motivate this to go full base on this. But what they're basically going to say is they're going to do 2 steps. So they're going to say use some sort of like empirical fissure, some approximation to estimate like how important each parameter is actually to solve your task. Of course, given that this is a super large neural network, they'll usually, if they do it very naively, they'll do like diagonal. If not, they'll do at least like k-fact. And then they'll use this to basically introduce a regular to your loss function. So your loss function on task A is just task A, but your loss function on task B is like whatever you choose the loss for task B to be, plus a term that's essentially some rate that you choose, some hyperparameter. And then the difference between the parameters at your state of at the end of A and the current parameters, here actually squared or L2 norms, multiplied by this Fisher information matrix, right? So basically this Fisher info matrix is going to have a high value for parameters that are really important. So those parameters that are really important, you're going to make sure that this subtraction here is actually as close to 0 as possible. So you want them to not change, basically, right? And of course, the intuition again is like, well, you're in a neural network with lots of dimensions, lots of parameters. You don't need all of them. And so try to make sure to maintain those that are important and sort of colloquially speaking, let loose all the rest, right? And so this is one way of viewing this. There is at this time, well, first there were a lot of follow-ups on this arguing tons of ways of why quadratic penalty is not a good idea, why it's not actually doing what this diagram is doing. That can be a different discussion. There was a second paper that kind of came out at the exact same time, was called Synaptic Intelligence, which is saying something similar, except for it's not going to do the empirical Fisher thing. So empirical Fisher is like you do it at the end of training, when you're like, or when you hope you're converged, and there's some like reasonable arguments of why empirical Fisher is meaningful to do. But synaptic intelligence is going to instead say, let's not do like these second order things, let's just acknowledge the taken trajectory, right? So if you see these cartoons and you go from like T0 to T1 to T2, it should matter like how you reach there, basically, like the trajectory should matter. At least that's how you can think of this in principle. What this paper does, in the end, is going to give a really, well, I don't want to weigh or judge this, but it's going to give a approximation, let's call it that. That's going to say that the loss you kind of achieve at the end, it's defined by like all the individual gradients and the changes to the loss they kind of made along the way. So it's literally going to sum over like all the gradients that you've had along the trajectory. And it's going to use that to basically argue you've randomly initialized the parameter, it's high dimensional, it's really unlikely to fit the solution. So the more change this parameter has experienced over time, the more important it must be. And then you'll use this again to form like a quadratic penalty term and so on. Right. No? No. This is but there, yeah.
I have a short one on something that you said you were going to talk about, like if the e-deficit is kind of like the Laplace posterior prior kind of thing. Is this similar to like taking into account some sort of like, but I mean, is this more similar to some sort of like Monte Carlo, the second when you look at the, because you're taking into account all the other like lower density points?
Sorry, I'm not sure about the Monte Carlo argument.
Because in the e-deficit, you're just looking where you end up, right, at the moment. And then.
Oh, sorry. No, you mean the second one being like this thing?
Yeah.
Probably, I mean, the way the people argue in the paper, at least in the motivation before they do something else, is like kind of like a path integral argument. I guess.
Yeah, I think maybe it doesn't fit.
Yeah.
So depends on the random initialization. A parameter is less important in one sample and very important in the other one.
Yeah. I mean, I have beef with these two methods, so I'm not sure how much I should say in the recorded version. Yeah. Right, and here's a slide that I just put these because I think it's interesting, just to like have that, despite me not being a neuroscientist or being like too qualified to talk about this. I think it is good to at least point to the correct papers to read if you care about this. So there are studies, and as far as I understand, they look at like spines in mice, and there are like changes being induced, and independently of this, they can measure that some of them persist for like a really, really, really long time. So like in a sense, like the neurons are being regularized very strongly, like they don't just all change. So some do, some don't. So it's this kind of idea that basically this quote before has said that there's this like pseudo-rehearsal mechanism going on in this complementary learning systems. But there's also a lot of like empirical evidence that regularization in this like update kind of argument is going on as well. So you'll find that machine learning people will also, they're very unlikely these now just do one or the other thing. Like they'll do something with the optimizer, they'll also do something with data storage, and then they'll probably combine it in some meaningful way. Like MT has a bunch of papers on this where this is pretty much exactly what is being done. Okay, and so these are like the two things that I personally think are easier to understand, and then there's a third one that Jonghyun called, I think you called this parameter isolation. I just call this structure because I don't really know what to call this, to be honest. You didn't call it, you referred to the survey paper that called it that, right? But basically what this is kind of about is going to be about, like, if you talk about neural networks, it's architecture, or in general it's going to be like model choice. And it's this idea that, of course, when we think of this forgetting, for instance, right? They're in neural network. It's kind of like a direct consequence of the fact that you have like overlap in distributed representations. So it's not like one parameter is exactly responsible for one concept, and then you don't have forgetting because you're not overwriting stuff. Is that like every parameter contributes to some degree to everything, and that's the thing that's kind of problematic. So you could also, at least that's what continual learning people are going to do, argue that you could try to reduce this overlap inherently, and then you would have to worry less about optimizers overwriting and data arriving over time, etc. The caveat, of course, to keep in mind here is that you could take this to the extreme, and you'll have very local representation in the way I've just mentioned it. Like you could craft a lookup table, but then the lookup table is going to have no forgetting because literally everything is going to have a single entry. But at some point you also set out to use like neural networks because you wanted to generalize. So there's some kind of trade-off in between there. Like it's going to be really hard to craft a lookup table and then easily generalize all sorts of things, right? So maybe there's some degree to which we want like overlapping representations, but maybe there's also some way in which we could at least limit this to a certain extent. So there are actually a lot of papers here that you could talk about, but I chose one specific one, again going back to Razvan because I thought he was going to be here. But I think it's also because it's intuitive to understand why this would help you forgetting before I tell you why this in general is a smart thing to think about, right? So there's this idea of progressive neural networks, which I think is a good thing to understand, where what you can say is like assume you have some model, like be it a multi-layer perceptron, convolutional network, whatever, and this has some hidden layers, right? Like hidden layer 1 and 2, and then it has an output. And let's call this a column of a model. Maybe you could call this like model 1, but it's basically a model you have, right? You learn task 1 with this, and then your task 2 comes in. What you're going to do is you're going to add a new column in quotations, or a new model, if you so will, that may be the exact same one for task 2 and another one for task 3. And you're going to randomly initialize them. Well, if you do it in this way, you just have 3 separate models and 3 separate tasks, so it doesn't necessarily help you at all, right? I mean, you're not going to have interference in the first model, you're not going to forget, but you're also not going to learn anything new, you're not going to leverage everything you've learned before. So, what the suggestion here is that in addition to these like bottom to top connections in this diagram, you're going to do like a kind of lateral connection, meaning on your column 1 or model 1, if you so will, you'll start connecting the hidden layers to the hidden layers of that next model, that next column in the next time step. So the information of task 1 will flow through task model 1 and give you the correct output, but it's also going to flow through like the second column, so that the model can now basically learn, depending on what the input of task 2 is. If that input were the exact same task, in fact, right, you might just learn to use H1 and H2 instead of, well, H1, the one in the superscript, right, like the task 1 in a layer, rather than learning a new one. If the data is super different because the task is like completely mutually exclusive, you'll just learn something new. The reason this helps is because in a sense it gives you something that continual learning people will refer to as forward transfer. So you'll be able to leverage what you've learned before in training the new thing. It will not incur forgetting because you don't have this like all-to-all connectivity. Like the connections in the sense they go like forward in time or forward in task if you so will. You're not connecting the second column back to the first one. The one bad thing about this is, if your task is in fact like extremely similar, you can't leverage like the new information to improve your old stuff, right? So you're kind of stuck with whatever solution you had. So you hope that that better be good.
This would assume that the learning rates are different.
Sorry, different where? Yeah.
In the columns.
The different columns have different learning rates.
There's a question, yeah.
I'm not sure this paper makes an assumption on this. I think it would be reasonable to not like set the same thing everywhere, but I'm not sure like this is what is mentioned in the paper. So can you specify like what? So what is the? So you have a new task, right? Like you're just training them from scratch in random initialized parameters. Like why do you need a like non-one learning rate or something?
Why should that?
Sorry, he said like he's assuming that the learning rates would be different.
Yeah. No, it was just a question because this kind of mimic what you earlier said was a good model that we have like we have a slow system and then we have a fast system. This is what you argued for earlier.
Oh yeah. So
So then your first column can be the slow one that is updated slowly, and you use that to kind of predict the fast one. And if that doesn't go well, you will change the task.
Yeah. Okay.
In that sense, they need to be different. I thought this was an answer to your question you have raised earlier.
No, I understand what you're saying. I think the reason I was confused is that like in this particular web, what they do is they trade one column, they like completely freeze it. So there's like no learning rate because nothing else is going done. It's just like fixed. It's not slow, it's fixed. But I understand what you're saying. Yeah, you could do variants of this. Absolutely. And I just added this slide in literally like 20 minutes ago in the other talk because I thought it's interesting because something came up. I don't actually remember what came up when we were talking about this. You don't have to think of this way, right? There are like tons of versions of how you can think about it. There is a paper that will maybe fit this workshop and better from the perspective. It's called like Continual Unsupervised Representation Learning, or curl for short. What they'll do is they'll still pick a neural network. They'll pick a variation autoencoder. It's going to give you latents, and what they're just going to do is like just make these mu's and sigmas, if it's like Gaussian, just make these different for each task. So don't like try to optimize the KL divergence to the same prior, but pick like task-specific priors basically, so you get that separation in different ways. But like your encoder, which is like the neural network, which is like the thing that learns the approximate posterior here, like it is kind of shared, right? So it is one way where maybe you can think of like, do you really want that kind of separation everywhere, or do you just want it in like specific places? So there are all sorts of like variants of these kind of models that you could now work with. In general, I find there are a lot of questions you would actually need to ask yourself if you use these models. So we did a work on this, but I'm not putting this out because of the work we did, but rather because the questions that are raised is, if you think about these columns, like if you don't have a human telling you exactly sort of this is task 1, this is task 2, but like it's some sort of like actual sort of real world problem where stuff just changes, you first need to realize like what is a new column, what is not a new column, like when do you add it, and you need to figure out like is this column, like how many parameters is this, like what kind of what goes actually on in here, right? Like how do you initialize that, like how do you set the learning rates and so on. So you'll need to ask yourself a lot of questions if you want to, in a sense, create neural architectures or other models that like expand over time. And the minimum ones you're going to need to ask yourself is the questions I just said, like when do you sort of add something, where do you add something, and like what is it that you're going to add. And if you're working with deep neural networks, of course you can ask yourself the question of, are you going to add just like parameters, or are you going to add like layers on actual functions, right? And so this table just lists a bunch of works, just so you have an idea that people are working on this, like a lot of people are working on this. But what I actually want to point out to is, like seemingly none of them have a very cohesive answer for these questions. Like they'll do very nicely in one regard, and they'll do like random in some other aspect. Or they'll do some like really sort of heuristic, like just do it everywhere or do it nowhere. So I'm not going to hog the tutorial, but I'm going to point to, we have this work called self-expanding neural networks. I was thinking about talking about it here, but I talked about it here already in September, so I'm not going to bore some people. And well, we're actually telling why we can answer these questions if you're going to like not using stochastic gradient, standard vanilla descent, but using natural gradients. You can expand your models on the fly as your complexity increases. So you probably anticipated the slide just for the sake of completeness, right? I just think it's interesting to see. Some people, I think, sometimes argue this whole expansion argument is like garbage. Why would you want to add parameters to your model? Like just take a fixed size model, like it's always constant and learns everything. In the mammalian hippocampus, there are new neurons being generated, and it seems like that this happens more in children, but it still happens in adulthood. So it's like new neurons get spawned, new neurons get integrated into the circuit over time as we learn, right? So in a sense, like all these three things I was just talking about, it's hypothesized that all these three things happen in conjunction in the brain, and all these three things typically happen in some combination in advanced continual learning works. Whenever I talk about this like adding parameters to model thing, I always think there is a really big disclaimer I should be making that doesn't get made in continual learning papers. Like you'll read, dynamic neural architectures are a way to solve the forgetting problem, sequential learning, blah, blah, blah. I was like, well, wait a second, wasn't it also that just, I mean, this is from one of the machine learning books, I think this is the deep learning book, just because it's kind of a nice illustration. But I mean, like anything we do, right, if we plot like the number of data points and they just increase over time, and we have, like in this case, some polynomial to fit that data, like the degree of the polynomial, like the capacity of your model, it just needs to increase the more complex, the more data you have. So, I mean, maybe these like column things, they help with forgetting, but also if you just keep on dumping more data of more tasks into your model, you also just need to increase the number of parameters that are actually able to fit this, or otherwise you're just going to run out of stuff to fit, right? So it's a bit tough whenever I see these like results and tables where they say like, oh, forgetting improved by this much, for me to distinguish like, is this actually because of forgetting, or is it because like you just ran out of capacity? And there's like some nice work by like Richard Sutton that was showing recently in a thing he calls like continual backdrop, that a lot of times when you perform poorly, it's just that you keep dumping too much, like you just run out of capacity. So it's, even if you keep training on the same thing, it just starts performing poorly. Okay, so this is the third thing. Maybe again, short interruption for questions if you so will.
I have the microphone. Yeah, while we're waiting, it's not still clear what problem or problems you're trying to solve. It's like there are several different approaches, and each seems kind of plausible for their own assumptions, but what problem do you want to solve, or what kind of problem do you want to solve with this continual learning?
Yeah, so I think, I don't think there's consensus, like, let's be honest. there's no consensus among continual learning people. If you were to ask me, I think what we're trying to solve is like, have one model, train one task, assume no access to the data anymore because, I don't know, storage costs, like privacy, whatever, and now train second task or like super like strong covariations or something. But remember both of them, like be able to perform on both of them when you later put in like test examples. That's if you were to ask me, right? So we started what, 5 past? So I have like 6 minutes. Okay, so as I thought, like there's a second part which is significantly shorter. It's more like an outlook. I can go through some of it quite shortly because I think it's just important to mention. It's called like Paradigms, Parallels, Prospect. But it's a bit like if you read continual learning papers, they'll tell you like you solve this catastrophic interference thing, which may or may not be a problem. You solve it all, and you can just like train on the real world and so on. And I think this is wrong. So, right, like you'll see these diagrams, like these are the exact 3 ways to think about it, where you can see like one is the importance thing, one is like joint training, one is like do partial sort of model columns, and one is like store examples. But you know there are lots of other challenges you will face, and lots of other setups you can think of that have like similar kind of ideas at the heart. I don't need to go through this in detail because Antti actually mentioned a bunch of this in his, I think it was in the BLR tutorial, where he said that instead of thinking about like time, you could also think about space. And there are other scenarios, like people call this fusion learning or transfer learning or domain adaptation. We've kind of surveyed this in this paper if you want to read about this. But I just want to zoom in a bit. Like if you look at some of them, like transfer learning, at least the way that Pan and Yang defined this in a very popular decided paper in 2010, it says like a domain consists of 2 components, a feature space and a marginal probability distribution. And then given a source domain and source learning task, a target domain and a target learning task, transfer learning aims to help improve learning of the target predictive function in the target domain using the knowledge in the source domain and source task, where there's some difference between the domains of the tasks, right? So if you think about this, like what I just presented sounds like almost exactly the same, or at least the answer I just gave you. And you'll find, it's kind of the point of the paper, when people say they like to do transfer learning and people say they do continual learning, it's kind of just the nuance of what they evaluate in the end, at least in my opinion. So this rule, it says like, aims to help improve learning the target predictive function. So basically learn faster, use less data, be more accurate in the target thing. Whereas like the continual learning person would say, well, don't forget the source, it's really important, right? And you'll find that future learning people will tell you, yeah, but you need like fewer data points. Domain adaptation is almost like the same definition, it's just gonna say the task stays the same, just the domain changes. And so there are these like, all these nuanced kind of versions that all create these like sub-problems in the literature that are probably all like very deeply connected or all made up, I don't know. All the way to the point where if you think, for instance, of like federated learning, like Antti mentioned this, you will also have these interference phenomena. Like if you have separated devices in space and they train on like 2 different data sets and you were to just like average the parameters naively, it would fail on like the exact same, or not, well, I shouldn't say exact same ways. It will fail also in like similarly motivated ways, having similar kind of issues, and you'll need to think about these questions, right? So this is just to motivate you. But I said I wanted to just like 2 minutes say there's a road to lifelong learning. So I just want to give you the thing like what's missing in order to actually, or what are some of the things missing to put this out in the real world, even if you got away with all of this forgetting stuff and so on. And it's really about the world being ruthless. So one challenge is like, I'm like trivializing this to just say outside the comfort zone, because I don't want to talk about like, is it out of distribution or all these like words that are hard to define. But here's a screenshot you probably can't read, but it's very simple. It's just saying, hey ChatGPT, please stop giving me any output. And well, you don't need to read it to be able to see that like it's performing pretty poorly at this, right? The second one is a video where someone's putting in, play? Oh no, because it's a PDF, I'm sorry. If the video were to play in a non-PDF on Hugo's laptop, the person is putting in like just A, like lots of A's, and then ChatGPT is spitting out like long, nice texts about companies and their internals and so on. And it's just like, well, I guess these systems weren't trained to abstain from outputs, especially these neural networks, right? So that's one of the problems. Like you put in some garbage in, garbage out, or you want nothing out, you'll still get something out. You can also think about, and this is what I said at lunch, I'm sorry, there are people here kind of maybe will get upset, no, hopefully not. No, there's also the thing of like, I mean, thinking about forgetting is one thing, but thinking about what you're dumping into the system over time is just as important, right? So there was this problem with like ChatGPT and other kind of generative models that like, if you say, can you produce a picture with 20 typical 7-month-old babies, it did very poorly on the covering the population side of things.
No, the mean is correct.
Well, or you could say it's doing the correct thing because it's just giving you the mean, maybe, right? So people were doing all sorts of things to dump in like more data to fine-tune on it. And I guess they were not thinking too much of like stability plasticity, so they added in lots of diverse data, and suddenly you ask Gemini to create like 1943 German soldiers, and they were anything but the soldiers that it should be rendered. Which is again problematic, right? So the things I guess you will also need to think about, which continual learning people kind of tend to forget somehow, ironically, but I guess when you talk about lifelong learning, you would maybe think about, are these questions on, like just look at the paper for the details, right? Like on curriculum learning, like how does the order and like the progressive difficulty of things affect your learning? So it's not just like, is it task 1, 2, 3 and you forget, but is it like task 1, 2, 3, or is it task like 3, 2, 1? It's gonna make a big difference. You can combine this with like active learning thoughts on thinking, well, you can dump in all the data, or you could also think about which new data points are important, which ones should you not include because they're garbagey. And you could think about, sometimes people call open world learning, what is known, what is unknown, like, does your model have a good uncertainty estimate? Does it, sort of colloquially speaking, understand which it predict and so on? So, we've written a survey on this, so I'm going to point you to it because it's just wrapping up, right? Like Road to Lifelong Learning. If you want to sort of, it's like a 30-pager or something. If you want to see how like forgetting is also connected to like active learning and like estimating unknown stuff, you could read it. So, conclusion, we've talked a lot about forgetting in continual learning, and there are a lot of like biological links. In the end, I guess this is kind of the joke at the end. If you want a real-world system like ChatGPT, you need to think about a lot of things, probably a bit of like everything, everywhere, all at once. And biological evidence in this nice work called Biological Underpinnings for Lifelong Learning Machines are actually going to tell you that like what humans, what brains, what like mammals do is a conjunction of different things. So it's at least like transfer and like rapid adaptation. It's also overcoming this forgetting thing, like the examples I've shown you. There's something about like exploiting task similarity and not caring too much about sort of these very perturbations when you change the order, and there's like noise tolerance and like resource efficiency. So this entire field is really tough in the sense of that there are so many ideas coming together that you can place a lot of small focuses, or you can easily get lost in like too many questions and you're not really sure what you're solving anymore. I guess that's just like my takeaway for now.
Hello, thank you. So yeah, I'm Tom. We're going to be talking generally about data acquisition. And the sort of high-level point here is we've got really good, in general, machine learning at utilizing data. Once we've sort of got the data, we can do some pretty spectacular things with it. But I would say we're sort of still a bit sometimes in the dark ages when it comes to actually collecting that data in the first place. We often have pretty crude schemes, heuristics are still often really the norm in terms of the actual data gathering process. So the sort of basis of this talk is going to be entirely around kind of how can we kind of think about doing that intelligently, and how can we kind of think about that data gathering and use sort of machine learning techniques and Bayesian techniques to make it so we gather better data in the first place. And that is basically going to mean we're going to talk about experimental design, because whenever we gather data, either we can't control anything and there's nothing we can do, or there's going to be things we can control, and those things we can control we can think of as designs. So anything that we're doing is going to sort of influence the data we gather, and what we're trying to essentially then do is sort of optimize those sort of decisions we can make, optimize those designs so that we can kind of get the best sort of data out of it. Yep.
Is it experiment design or experimental design?
I would usually say experimental design. I think either is fine. I usually say experimental design because it's going to become adaptive and things, and it's maybe not just designing a singular experiment, but it's So sort of depending on context, there's lots of things we might have. We might be, say, doing sort of clinical trials, and we want to sort of figure out how do we set up that clinical trial. We might be doing surveys, what questions do we ask, and things like that. Or we might have a classic example of active learning. We might have lots of sort of unlabeled data, and we're kind of thinking about which sort of points to gather labels for. So all of these at sort of big level, they're all going to kind of come under this kind of big experimental design framework. So to sort of get us started, I'm going to use a very simple example of the kind of problem we might think about. And we're going to be we're a psychologist, and we're going to be asking people about money they want and their sort of subjective values of money. And we're trying to choose the best questions. So we might ask people, do you want sort of £60 a day or £100 in a year? That's one question. Another question we might ask, do you want £200 a day or £100 in a year? And it's kind of obvious that one of these questions is a lot better than the other. So this sort of second question, everyone's going to kind of answer the same thing. So if we've got someone who has maybe a problem with drugs, they're going to sort of say, yeah, I want £200 a day, and they're going to want to say, for the second one, they want £60 a day. Someone, maybe sort of retired professor, but again, they're going to want £200 a day, but maybe they want £100 kind of later. So we can sort of see that the second question is sort of better in a sense because different people are responding differently. It's kind of more informative, and we're kind of getting more feedback from this. So we have this sort of notion that kind of informative of the question. And we can start thinking about that by kind of formalizing it, and we can actually do it in a sort of a probabilistic way. And in particular, we can start reasoning about beliefs, and we can sort of talk about kind of information that we might gather from that data. And this is sort of really fundamental, because if you actually go and look up what is the definition of data, the definition of data is something that conveys information. And so what we want to say is, if we want to say how good is our data, we're really saying how much information is that data containing. Of course, there's maybe things like bias and fairness represented as well, but sort of at its core, what we really need is a lot of information in that data. And so what Bayes is going to turn out to do is it's going to give us the sort of the groundwork to sort of formalize this and talk about how much information have we gained from observing some sort of observations, observing some data, and from that we're going to be able to sort of push that back and use that to sort of figure out how should we sort of set up our experiments. So the basis of the talk is this idea of Bayes experimental design, which we could also call an information theoretic approach to experimental design. And at a very high level, what we're doing is we are choosing designs. I'll be using Kai through the talk to refer to those, so that whatever data we collect, I'll use Y for data, is going to be as informative as possible about some sort of target variables feature. So this last one needs maybe a bit more explanation, because this could actually be lots of different things. So maybe we have a Bayesian model and it's the parameters of the model. But maybe we're doing active learning, and actually really what we want to learn about is predictions we're going to later make. Or maybe we're doing a clinical trial and it's not necessarily our model, but it's some sort of thing that the clinical trial has been used to assess. So we're going to basically get most of the changes of how we can do things and things by sort of carefully figuring out what the thing we want to target in. If we can target information in the right thing, we've got this sort of good basis to now kind of design our experiments to be as informative as possible.
You are allowed to do this adaptively.
Yes. Yes.
That's the key thing, yeah?
Yeah, so we can absolutely do this adaptively. I'll progress up to that, but I'm going to sort of talk first about what we want in a static setting. We'll work up to see how we're going to do this adaptively.
Because that question will be different if you do it in the Bayesian context and doing frequentistic. Because doing frequentistic would be hard to justify doing this in adaptive way, that would be harder.
Yeah, exactly. This is basically one way.
Yeah. Sorry.
Okay, so yeah, pretty much almost immediately. Okay, so the starting point I'm going to argue is that if we want to do any of this, what we really need is some sort of generative model. And the reason we need some sort of generative model is if we're reasoning about the future, we need to actually have some way of sort of simulating the future. So this is not like in a machine learning case where I can kind of go and just do something completely discriminative and I'll just be okay. Because we're reasoning about sort of things that are coming in the future. We need some sort of modeling aspect. Even if we've got that model in a data-driven way, even if we've taken something, trained it with loads of data, we're still then treating this thing as a generative model when we reason about the future. So this key is this sort of generative model in particular. It's going to be a generative model over what data we might see, what we're trying to learn about, these sort of variables of interest theta, and it's going to be sort of conditional on our kind of design choices. So this is essentially a model for our experiments. It's a model to simulate what data we might see. And if we kind of don't have this, at least have something implicitly that's like this, there's not much we can kind of do to go and kind of do things intelligently. Thankfully, though, it can take a lot of different forms. So it could be some sort of classical simulator. So we work sometimes with sort of climate scientists, and they have sort of old school scientific simulators that we can use. It could be things like the classic SRI model from epidemiology. So say we're trying to do COVID testing, we're trying to figure out who should we test, where should we test. There are sort of classical statistical models that we can use. Or it can be machine learning algorithms. So a classic sort of case of Bayesian experimental design is Bayesian optimization. And in Bayesian optimization, usually we take a GP as a model. It could also be a neural network if we're, say, doing active learning. So there's lots of flexibility, but the key is we need to be able to kind of actually have this model. Once we've now got this model, we kind of now actually have basically everything we need. Because in the same way that we've sort of got this universality of Bayes' rule, we've also kind of got a universality of kind of information as soon as we've got this kind of generative model. And in particular, we can define something called the information gain, or the Shannon information gain. And that's going to be a function of our design and what data we can see. And this is simply the reduction in our uncertainty, or more precisely, the reduction in our entropy when we make this new observation. So when we get some new data, we're going to sort of update our beliefs about our variables of interest. And so we have an uncertainty before, a prior entropy. We have an uncertainty afterwards, a posterior entropy. And this gives us the Shannon information gain. And at this point, we see something that's sort of quite inherently Bayesian that's sort of sprung out of this. This is a prior, this is a posterior. This is the difference between our prior entropy to a posterior. But we don't have to sort of formulate this from a Bayesian perspective per se. We've just got this like, sort of information. If we accept we want to work with Shannon information, this is kind of automatically going to come out. And there's reasons we wouldn't want to do Fisher information here, because Fisher information is kind of the wrong style of information. It's not the kind of information about how much we know about some parameters. It's kind of a precisional information. So, for example, if you were to work with Fisher, you could get infinite data, and you could still sort of keep thinking that you're going to get more information, even though you've kind of collapsed. So there's sort of quite inherent that if we want to use information theory, and we know we want to use information theory because data conveys information, then we kind of end up pretty much with this kind of Bayesian thing popping out. Unfortunately, though, of course, we can't actually deal with this directly. This is a function of our data. We don't have that data yet. So we want to sort of have lots of information, but the information is a function of the data that we don't yet have. So what we now need to do is work with something that we can actually evaluate. So instead, what we do is we take the expected information gain. So we're just simply going to take an expectation of this information gain over some distribution on the data we might see. And again, here now we need some sort of modeling. So we needed a model to define the information gain, because we needed some way of defining our beliefs, and that requires some kind of model. And now we need a model so that we can kind of simulate the possible data that we might see. So typically, we're just going to take this as sort of marginal, and the prior is kind of almost the prior predictive that this is sort of defined with respect to. So it's before we've seen our data, if we have a model, this under our model is the kind of best distribution we've got of simulated outcomes, and then we're going to use that to take our expectation over here. So we get this final thing, which is that the expected information gain, which is going to be the kind of key quantity we're working with throughout the talk, is an expectation over the possible data we might see, of our reduction in our uncertainty of these parameters of interest, where we're using the Shannon information to formalize that. We can then say that our optimal design is simply the maximization of this expected information gain. We're just simply trying to find what designs in expectation will give us the most informative data that comes back. And what's interesting is that there's actually lots of different views to this, which sort of nicely fits in with the kind of duality aspect of the workshop, is that there's loads of different forms that this quantity can take. So the one that's maybe sort of most clear-cut as almost the duality is it's also turned out that this is the expected reduction in predictive uncertainty. So we can actually take an expectation over a sort of parameters. So you could write this as expectation of theta of a change in entropy, or you can write it as an expectation of the joint of your model of the log likelihood minus the log marginal. So this is sort of an expected reduction in predictive uncertainty. So we can have this dual between how well can we predict, the same thing as how well can we actually sort of learn about our parameters. Other things is that this is actually exactly the mutual information. If you want to say, I'm going to maximize the mutual information between what I'm learning about my data, that exactly gives you the expected information gain, because you can't have a mutual information without a model. You can't actually define this unless we have some kind of model. Finally, you could also think about it as some sort of utility that is a KL divergence between a prior and a posterior. So we can think about this as which sort of design in expectation maximizes kind of our expected KL divergence in between this prior and the posterior. Okay, this is probably a good point to just pause for questions.
Yeah, I think I know the answer, but just to clarify, so wherever you write the prior here, right, I guess in the case where you do it adaptively, like that would be the kind of last posterior you've had from the previous data point so far, right?
Yeah, you're basically one slide off. Yeah.
Yeah, I don't know, maybe it was a little bit slow. Like the second formulation makes a lot of sense to me. And then, so basically they're all equal, like you just need to do it.
Yeah, it's just Bayes-Duality. So if you start with this, and I can cancel this so it's py given theta, and that will give me this form at the bottom. I can cancel it so I've got p theta given y, and that will give me the form I just gave before. So they're all just sort of manipulations of the original form. It's worth pointing out that the original form I gave is in some ways, this is the most pure form. And the reason it's the most pure form is that this information gain is the quantity we care about. This is kind of, if we've got some belief system, this is sort of the optimal thing. And here we're actually making an approximation. Here we're sort of using a model to make an approximation to simulate data. So this form really tells you where things are breaking down. It sort of says this, if we have this model, is really what we want, and we have to make an approximation here. If I now took this and didn't use my model, if I used a different distribution on my data here, which you sometimes do, then it would no longer equal these other forms. So these other forms are sort of, in a sense, slightly less pure than the form I gave.
So in what sense is this an approximation? Because you don't have the data that you possibly could get, so it's not an approximation.
It's an approximation of the true world. So there is a distribution of data.
To the model.
So your model of the current world, and there is for as an approximation. Whereas this is our belief system. This is truly kind of what we care about. In particular, if we're going to do a Bayesian analysis when we're done, this really is the quantity we want to optimize.
Yeah, but there is not an approximation of that. It's just that you're not able to model the real world perfectly.
Yes,
exactly. That's another approach.
No, just not a short question because we just. The thing is, I understand how the KL is.
Yeah, it's good.
Like it's well defined, but would the information gain always be well defined? Like I'm just a bit scared because differential entropy, like it could be like infinity, like you can have this. So I thought it'd be kind of the opposite. Like the KL wasn't the more nice answer quantity.
Yeah, so this takes a little bit more maths, but your information gain is never negative. And basically the way, actually it doesn't take that much more. This is never negative because that KL is never negative, so its expectation is never negative. So it's harder to see from these other forms, but if you look at the fact that these are all equal, you can see that, yeah, you'll never get negative information. What is interesting and what is important is the information gain can be negative. It's only the expected information gain that is strictly positive, but you can actually learn less. So a good example of this is, say you're modeling and including some modeling of the variance, and you get an observation that sort of tells you, oh, actually there's more noise in my data than I thought, then suddenly you actually would have your uncertainties increase. So you can actually have negative information, you just can't have negative expected information. Yeah.
So regarding the second equation with the KL, so the mean KL distance, do you have any thought of instead of using a KL, for example, an reduction of distance? Because so a KL can be quite flat on some places. For example, washer time or.
Yeah, so there are things that you could do here. And I'm trying to remember which one people have done. So the way people usually change it is slightly different. They would usually they sort of view this as kind of a utility, and that there's kind of different utilities you can set up. So maybe a good example here is Bayesian optimization. So here, the KL gives you the kind of information theoretic version, but if you did Bayesian optimization, you want to do expected improvement, this could be kind of formulated in this kind of setting here, where you replace that KL with something like sort of expected improvement. Yeah, there are issues if you change that KL to other things in some ways, because you lose a lot of your kind of tricks that you can manipulate these around, and there's a lot to be gained from that KL. And I think someone said earlier that the KL is your sort of pure thing, and I would very strongly disagree with this. I would say that this is the explanation for why the KL makes sense, I would say, because it kind of comes out of the information. The KL is not the starting point, but this is the starting point, and this shows me that the KL can make sense here as my utility function, because it's the utility function that then relates to my Shannon information. Was that a question, Phil?
Yeah, is there, so like, suppose it's your simulator, or what do you call that? Simulator is wrong. Is there some formulation that makes more sense than the other in that case?
We're working on that. Yeah, it's not been investigated enough. So when I get to the end, I'll talk about future directions, and the big issue with all of this is model misspecification. And one of the things there is it's unclear how it comes in. What you'll see though is we will have a lot less flexibility of which of these we use than you'd expect. Just to sort of poke ahead, this thing is doubly intractable. So there's going to be real issues to work with it, and we're going to end up with quite particular forms that come out. So we can never estimate these quite directly. We're actually going to have to make completely different, sort of more sort of nuanced estimators.
One quick question.
Yeah.
So, do I understand it correctly that if my posterior collapses, then the information gain will be large, or because then the entropy will go to minus infinity, or?
Yes. Generally, it gets a bit more complicated. That usually it will not run off to infinity. Actually, let me be more precise. If I have lots of observations, you will end up with your overall information from your big stream of observations will go to infinity, but the incremental information you gain from each new observation will go to 0. So you'll have the sum of things where each term goes to 0, but the sum goes to infinity. So in short, yes, you want a very sharp posterior. In terms of what happens with infinities, it gets a bit more complicated.
Okay, then as a follow-up, I mean, isn't it sometimes not quite bad that, let's say, my posterior collapses to some really bad states, then it seems very greedy, I just want to collapse my thing, but
if I collapse onto something stupid, then that's a very bad outcome. So
Then you shouldn't do Bayes.
I can carefully select my information that I maybe collapse to something.
Anytime you do that, anything Bayesian, you're subject to this. So it's true, but that basically means your model was not rightly set up. You've not set things up in a way that actually reflects how you want to do it. This is, I think, a hidden issue that's always there in Bayesian modeling that people ignore, and it's just explicit here. But I'm not introducing something new. This is a fundamental issue, I think, with Bayes. This is sort of hints at sort of non-parametrics and things as well, kind of what happens when this collapses. Is my model good enough? Sort of hypothesis based, but yeah, that's probably a rabbit hole we don't have time for.
Okay, thank you.
Okay, right, so hopefully everyone's now at this point sort of on board. We've got this notion of sort of expected information. We have a particular sort of expected information objective that we want to work with. And this is kind of useful in itself. Sometimes there's definitely cases where you just want to set up some experiment and you've got a big model and you want to optimize it. But I would argue the direct use cases of that are not too there's not too many of them. But where it gets really useful and really important is when we start thinking about being adaptive. So what we really want to do is that we're not going to gather all our data once. So we've just gone through, say, continual learning. Good examples that we sort of often gather data bit by bit. And in that we have sort of ability to action how we gather the next bit of data. So as we learn, we want to continually learn how to gather new data. And the sort of Bayesian experimental design framework actually fits beautifully into this. And I'm going to start calling it sort of Bayesian adaptive design in this kind of setting. And the idea is just going to be, for now, is going to be really simple. I'm going to sort of change this a bit later. But for now, we can kind of think very simply. We can sort of say, well, what we're going to do is we're first going to run this design. We're going to optimize this expected information gain. That'll give us the next design. We'll run our next bit of experiment. We'll get our new sort of observation. And then we can update our model. We can do, say, Bayesian inference, and that'll give us a new model. Or we could do a frequentist update, but then we'll sort of have some kind of mismatch in our decision making and what we actually do. But we're just generally, in some sense, going to update our model. Once we've got an updated model, we can then re-optimize the next design, and we have this sort of nice, sort of self-fulfilling system. And again, this is where you can kind of see how Bayes can come in quite nicely, because it's always iteratively incorporating our beliefs into our model, and as we iteratively incorporate our beliefs into our model, we're gathering information, and therefore we're sort of learning, and then we're targeting the new, novel information that we have to get to the next step. So, for example, if we go back to that sort of question asking case with the sort of psychology, we could think about kind of saying, well, we're going to ask first question, get our first answer, we'll update our model, and then we'll optimize to get question 2, we'll get a new answer, and so forth. So you can now think about having an adaptive survey. Instead of sort of setting the questions we're going to ask, as people are asked questions, we get their feedback, and then we're going to update their questions. We're going to sort of hone in on them. So for, say, this person that has an addiction problem, we're going to sort of offer them sort of increasingly sort of small amounts of money now compared to the future to sort of really find their kind of trade-off point as effective as possible. And what we're going to find is that this EIG term we've worked with is going to be really nicely just sort of updatable. We can basically do the normal Bayesian thing and take our old posterior and make it our new prior. So here, H is something I'm calling the history. So this is basically the set of designs and sort of observations that I had so far. And all I'm going to now do is replace my old prior with my posterior at t time minus 1, i.e. p theta giving ht minus 1. And then I'm going to look at now, okay, what's the expected information gain at the next iteration? So we get this sort of incremental kind of EIG, where we've updated our model, this is defined a new AG, and we can look at the incremental information we're gaining over the next iteration, given what we've seen so far. So the key is we're learning now on the fly. The model has already incorporated the information from the previous data, and given we've incorporated that information from the previous data, now what's the next decision that we should be going to make given that? And so this sort of gives us now a framework where we can say, as I said before, we can optimize the designs, do the observations, and now we could just think about this as all we need to do is a posterior inference update each iteration. That gives us our new model, and now we have a sort of a fully defined system, and the only thing we had to specify was our generative model. Everything else is sort of coming out of this automatically.
This problem, I use the model to require data. Is it still, it's right as part of this IID, or is it
Sorry, could you...
So if you acquire data by the model, under the model basically, is it still IID that's connected by this product here, or is it there
It is not generally IID. So this is probably a more complicated question than I can answer right now. This is easy to see in like active learning context. So generally, if we're being Bayesian with everything, we're going with the likelihood principle. It doesn't matter that the data is not IID for it. It's not actually messed it up. If we're now training a frequentist model and doing empirical risk minimization, this can be a problem, but it's easy to correct. So we actually had a paper 3 years ago that showed that there is a relatively simple, it's hard to derive, simple to calculate kind of set of ways of weighting data points that kind of can recorrect this kind of bias. But yeah, and I think this is maybe one point to maybe discuss a bit more actually, because we never think about this when we do analysis. We always say the data came from something, and we always say, oh, there's this IID beautiful thing. It's just not true. Data never came the way you thought it came. And I've not done anything here you ever think about. I've just sort of, you never think about where the data came from in your analysis, but this has just made it obvious that that's problematic that you never think about that. And yes, it will cause an issue to not be ID, but your data probably you've never really seen ID data anyway. And similarly, there's no such thing as randomly choosing data. That's rarely a well-defined thing. You can say, oh, I can just randomly gather it. That doesn't really happen. This is sort of where you get data set biases coming from, lack of representativeness. And we really need to think more about this beyond even just the information stuff I'm talking about, but for sort of fairness, bias, all the rest. We ought to think more about where our data comes from, because it never really is some true unbiased IID thing.
I mean, I think this kind of makes an assumption somehow and goes back to my modeling correctly, right? So if you explore according to your posterior uncertainty, somehow eventually you do the right thing or you correct it. Eventually something is messed up. Maybe there's a way to correct it, but it also almost feels wrong in the sense that if things didn't go as I expected them to go, then the data collection mechanism should have some room for that, right? Randomization is something, or at least something that corrects me or gives me a way to, I don't know, you see what I'm saying, right? And it doesn't appear naturally bad. So is it really bad?
This is definitely a problem, and this is a lot of what the research front that we're really trying to work on at the moment is around this kind of model misspecification, what happens when things go wrong, and this is quite difficult to do, and you've kind of got this issue essentially that you're using a model to gather the data, and you're fitting your data to the model. So there are things you can do. The simplest thing is you can just change your model halfway through. So particularly in say like an active learning setting, I can just go retrain the model, and that's fine. It means that one step I didn't quite target the objective. So essentially what we're doing is we're targeting my expected reduction in uncertainty under the update I make. And we're sort of implicitly assuming making a Bayesian update. If I don't make a Bayesian update, there'll be a bit of a gap, but I can always change it. So this is sort of, I agree, but this is almost a sort of a continual learning problem, basically. It's kind of what do I do with my model as I get more and more data? Yeah, again, I don't think it's something that being adaptive with my designs is in self-making, but it is certainly something we have to think about.
So about this point, a good Bayesian would never say Bayes is bad in such a case, right? Like they would say, like, oh, I should put a prior over my model or something. Do you investigate such a case where you put the priors over models, and then as you can then update your model also, right?
Sure. I mean, this is just another model, but it does get more interesting because when I'm a Bayesian modeler, I can kind of just use an uninformative prior, and I don't usually pay too much because essentially I'm hoping as I get some data that will kind of go away. Here I can hear huge issues for having an uninformative prior because you're sort of taking an expectation under your prior predictive, you're simulating data. So if your prior is super uninformative, you're going to have super uninformative decisions being made. So it's actually more critical than you would expect because of this fact that sort of you've got to make a decision, you're being a bit more committal. And so usually we do this to hope that the data will just sort of speak for itself and correct things, but we don't have that kind of luxury here all the time. So I think it is a bit more challenging.
Maybe it's kind of more like a general question. So basically, it seems like the system is kind of like recursive in some sense. You have like a circle that basically is kind of like, and basically in this kind of system, like basically you also define like each step of the dynamics. But then I'm actually kind of interested, is there like some kind of guarantee about this being stable, and is there some kind of analysis like the asymptotic, like regime?
So yeah, okay, so one thing is I'm going to actually break this later, and then it will be a different scenario anyway. But yes, is the short answer. So Liam Paninsky had a paper back in like 2006 that showed if your model is well specified in the like very formal sense, so there is a true theta where py given that theta is the true data generative distribution, this will still satisfy Bernstein von Mises, and therefore it will sort of converge. And it will provably do it quicker than if you sample data at random. So, yeah, every bet is off if your model is not bad. But if your model is well specified, this is basically provably, essentially the best thing to do. I could have done this a bit differently. You could formulate all of this as this is the formulation of what optimal decision making is, essentially. And what we're going to do later is we're going to see that there is an issue here, and what's the issue is greedy, and we're going to stop it being greedy. And once we stop it being greedy, that is sort of formally the optimal way to make the decisions. Okay. Yeah.
Well, given that all our models always are ill-specified, and in fact we don't usually care about the model, so if you're using a neural network, for example, you don't care about the weights at all. It seems that maybe the goal of reducing entropy in theta is the wrong one. We should be increasing predictive accuracy or reducing information in the predictive distribution I want.
Completely correct, we wrote that 2 years ago. It's called predictive oriented Bayesian active learning. I never said here theta was your model parameters. So theta can be anything. And what you do is you make theta, instead of theta being your model parameters, theta can be downstream predictions. And then you get something we call the epic score, and the epic score is then the expected predicted information gain if I want to do active learning. But at the same time, I might also be doing a clinical trial where it's not prediction, it's really theta, and I'm actually doing stats, not machine learning, so it varies on context. Okay, so there is a big issue here though. These things are very slow, and we just saw a good talk about how we might try and do sort of that inference thing quite quickly and things, but the design is also really slow, and this is going to be very restrictive of where we can use it. And so the sort of historical viewpoint on Bayesian experimental design is that like this is a wonderful formula and this sort of tells us optimality in our decision making, but it's completely useless. And it's completely useless because it's just sort of so horrifically computationally intractable that we kind of just can't really do it. So like even if you go back 6 years, people were doing this with models with 3-4 parameters and design spaces with 2 or 3, because that's the maximum you could kind of get to. So we've got some stuff we've got to have to go and correct if we actually wanted to go and do this. So the first really big issue you've got is that this expected information gain is not a sort of quantity we're used to, it's a doubly intractable quantity. So we cannot go and just do stochastic gradient descent on this. We can't just go and do Monte Carlo on this. So that this posterior, this is intractable, and then we've got an expectation of that of the log of this intractable thing, and then we've got an expectation of that. So this is super nasty kind of thing to actually work with. And so it's easier to see this if we flip and use a different form. So remember, I had all these different equivalent forms. One of them is this, the expectation of the joint of the log of the likelihood over the marginal likelihood. And let's just say we're going to do Monte Carlo for this. We're going to take some Monte Carlo samples of the outside, which I can do. This is a joint. So I can go and I can make my Monte Carlo estimator. And let's look at each term. Well, I've got the log of the likelihood, that's fine, unless it's implicit, but most of the times it won't be, so it's okay. But then I've got the marginal likelihood. And the problem is it's not one intractable term. Each sample is its own intractable term. So the more samples I draw, the more intractable problems I make. And so this just gets nastier and nastier. And there's no simple trick to sort of just make that suddenly go away. This is a sort of a strictly more difficult class of problems than we're used to dealing. It's more difficult than an expectation. It's a nested expectation.
What do you mean by intractable?
I suppose I'm using it a little loosely. What I mean is you don't know this, so I can't directly evaluate this Monte Carlo estimator. So as n goes to infinity, it does not converge.
I see. So from meaning that for the bottom one, you have another integral there? Is that what it is?
Yes.
Okay.
Yeah.
I see. And that's sitting it's somehow in the ratio, and that affects, I see.
Yeah. So it's 95% of machine learning with either sort of estimating or maximizing expectations of functions in some way or another. This isn't that. This is an expectation of a function of an expectation, and you cannot just move that expectation out to the front. So we need to do some clever stuff to get around that.
But I mean, if you think about why, sorry, I'm taking your time, why these things arise, right? So one is over theta, and then somehow you also have to simulate what kind of data will come in. So they are two different things.
So the problem is yn. And when n increase, you get more and more extreme. So then you have to estimate the marginal likelihood for more and more kind of extreme events. And this is close to zero. And to get that right, we need even more. So the worse it gets, the more you get, and then it's kind of.
So yeah, it's essentially the same thing as Bayes. We either have this intractable posterior, or we can think about it as an intractable marginal likelihood. So I could have flipped this round, and I could say, oh, I've got a posterior I can't deal with. Or I can say I've got a marginal likelihood I can't deal with. I'm going to kind of explain it a bit more anyway here. So the naive thing we could do is we could do a Monte Carlo estimator for that. So we could do what's called a nested Monte Carlo estimator, where we just, each time we have a new one of these, we're going to draw m sort of samples here, and so we've got this sort of nested estimator inside the other. And each of our outer samples have its own little Monte Carlo estimator that's living inside. And surprisingly, this thing is very inefficient. Our budget is m times n. We showed sort of 6 years ago the best possible convergence rate you can get for this is order t to the minus 3 in total cost, compared to t to minus a half that you'd be used to if you're doing normal Monte Carlo. So this is sort of quickly, completely intractable. This is sort of, unless you're using very small numbers, this just gets sort of really horribly bad. So to sort of solve this, we have to kind of think about sort of what's going wrong. And if we think about it, what we've really got is something where each of these Monte Carlo estimators is a separate estimate of a particular evaluation of a function. So my marginal likelihood is actually a function of the data I can see. And if we're doing these separate Monte Carlo estimators, these are just sort of essentially separate estimates at each possible value of y. But if you look at it, there's an obvious thing to do. We can treat it as a regression. If we can actually learn that if we do a density estimation or regression, and we think about this as learning a function, then they're all going to start talking to each other. So as I draw more of these, my function estimate gets better, and as I get more and more samples, the error in all of them can kind of go down at the same time. So what I'm going to do is I'm going to sort of think about it more as a two-stage kind of procedure. And first, I'm going to take my marginal likelihood, and I'm going to say approximate it, a bit like some sort of variation approximation, say, and then I'm just going to plug it in. So I'm going to sort of get rid of this intractable thing and do it as a function estimation, and then I'm going to go and stick that in, and then I'm going to do a Monte Carlo estimate with this approximation here. And this turns out, quite coolly, to actually give us a variational bound. So it turns out it doesn't matter whatever approximation I put in here, this is always going to overestimate my actual EIG. I actually have a true variational bound. It's a different variational bound than the one you're used to, but this is a true variational bound, and it's tight if this is the same. So if I get the correct marginal likelihood approximation, I will get exactly the EIG. And for any estimate, it's strictly going to be above it. So we can actually start doing this like we might with variational inference. We can actually do the estimation by minimizing this with respect to phi. And we can just do that as a minimization. And in fact, there's loads of bounds that can work. There's not just this one bound. So we, instead of approximating the marginal likelihood, we could introduce an amortized inference network, and we'll get something that looks a bit more like a sort of a VAE. So this is something called the Barber-Agakov bound that was introduced in sort of slightly different settings by David Barber, and I'm not sure what Agakov's first name is, in Europe 2003. There's other things we can do. We can go and we can introduce an importance sampling estimate for that marginal likelihood, and any importance sampling estimate for the marginal likelihood, again, gives us a valid bound. We can also, instead of making it an importance sampling estimate, we can include the sample from the top as well. So if you sort of have, we have one feature sampling on the outside for the likelihood, I've got loads and sampling for this. And if I include my zero sample, I get a contrasted bound. I get something that is a generalization of things like the info-MCE that you see in a lot of kind of deep generative model cases. And in particular, what's cool is I can actually get bounds both sides. So if I've got this sort of zero sample, if I include it, I have a lower bound, and if I exclude it, I have an upper bound. And so I can kind of start playing around a bit with this. In fact, I can also sort of use more samples. It's kind of like I-way. If I increase sort of M, I can kind of artificially tighten these. And so there's this whole sort of family of different bounds we can use, and we can kind of use different ones in different kind of settings. And these things are going to be much faster, because basically, instead of doing everything multiplicatively, we're now sort of additive. So we're now sort of solving this kind of problem that was a sort of functional estimation problem, and that's going to cost us sort of order m. And then once we've got it, we're going to do some sampling. That's going to be sort of order n, number of samples. So we've gone from kind of this multiplicative cost to this additive cost, and this is going to basically give us really big jumps in our performance. And in fact, it's going to fundamentally change our convergence rate. So the sort of traditional nested Monte Carlo approach will converge at order t to the minus a third, and this variational approach will converge at t to the minus a half. So if you're thinking, oh, this is sort of variational versus Monte Carlo, it's not. This is strictly better. It's not comparable to the inference setting. It's a strictly better convergence rate. Both are biased. All nested Monte Carlo estimators are biased, unlike normal Monte Carlo. So here it's a pretty strict improvement we've actually been able to gather by kind of switching to this sort of dual approach, this variational approach that's going to exploit things. And in fact, things are going to get even better actually when we look at it in this variational framework, because what we're trying to do is actually optimize this thing. I've just so far been talking about how horrible this thing was to estimate, but actually we're optimizing it. And if I have this nested Monte Carlo thing, I've now got this almost sort of black box objective I'm going to have to kind of wrap around. But if I do a variational thing, something beautiful happens, which is that the maximization of my expected information gain with respect to designs has the same optimum as the optimum of my variational bound that is jointly optimized with respect to variational parameters and designs. So I've essentially now moved things into sort of an augmented space, and provided it's a lower bound, so there's different bounds, some are upper, some are lower, provided it's an upper bound, I can just now do this as a simultaneous optimization on these two things together. And so this is going to keep sort of going, because now we're doing stochastic gradient methods, things are going to start scaling. So this is suddenly going to kind of start working for kind of high dimensional problems, and lots of other sort of benefits as well. There is a quick interesting sort of side note with all of this. So we've kind of, these variational approaches give us this nice way of, essentially we've circumvented a double intractability by this kind of augmented space. There is, turns out, it came out from researchers actually in Tokyo a couple of years ago, that there is a Monte Carlo solution to this as well, with something called multi-level Monte Carlo. So if you're not familiar with these, I think they're quite interesting. They're definitely sort of the most black magic thing I've ever seen, I think, which is that you can make something biased unbiased by kind of taking these infinite sequences. So you can kind of essentially do an importance sampling on a length of an infinite sequence. And if you can make something into a sort of a conversion infinite sequence, there's these really crazy ways that you can suddenly make it unbiased. And
there is a but.
There is a but, but maybe the but is gone. So the but is that usually it's infinite variance. So to start, most of these things are infinite variance. Yeah. But what they did 2 years ago is they made finite variance. So there is a specific estimator to this case. Okay. So some guys here in my PhD student Adam together managed to sort of show that there is a very particular way with some careful antithetic sampling that you can actually get the variance finite. It's probably still much higher variance than the variational estimator, but it does now give you something that is a sort of combined Monte Carlo thing that you can then again do stochastic gradients for.
Yeah, because normally when you get this kind of, you're simulating this event to getting unbiased, but the expected value is fine, but you pay by infinite variance. This is the first time I see you have finite variance in the, you can actually make it right.
Yeah, this is why it's black magic. It really goes against your intuition. You have something that is like, you sort of almost fundamentally shouldn't do, but it does sort of work out. And it's essentially, you have to have this sort of coupling on your sampling that means that it sort of, you overtake the variance increase with this coupling and sampling, and it overall means that it sort of starts to decrease. So you've got this infinite sequence, and the problem is as it gets longer, the variance goes up, but with the antithetic sampling, as it gets longer, the variance goes down, and therefore the overall variance actually ends up being finite. Anyway, so this was a bit of an aside, but the high-level thing is there's sort of now these two ways that you can kind of circumvent these doubly intractable problems that sort of, certainly when I was doing my PhD, I kind of thought we would never do. I didn't think you could kind of get around these, but it definitely sort of turns out you can. So are we done? So let's go back to our example. Okay, we're going to ask someone, do you want £90 today, £100 in a year? They say £100 in a year, and you tell them, I've done some great stuff, and like it's going to be really efficient. It's this really efficient estimate, but I am still running an optimization. So you are still going to have to wait 15 minutes before I ask you another question. And so even though we've sort of really made these things efficient, we're still in kind of a bit of a problematic scenario. And in particular, it doesn't really matter how quick I make my optimization design, I still have some inference I had to do. I still actually got a model update to do. And I'd really rather not kind of do that. I'd really sort of prefer to get that thing out of the way. And so what we want for most sort of these problems is we really need to speed this up. We need something that will actually go and work in real time. And to do this, what we actually have to do is we have to go back. We actually have to reimagine that design pipeline itself. We have to sort of say, well, this sort of thing of choosing designs, observing, updating our model, that kind of needs to go, because that framework itself is already problematic. And what I want instead is I just want to stick a neural network in there. And I want to have that neural network sort of take in my data and give me my next design decision. But it's going to turn out we can do that really quite surprisingly principally. So what we're going to do is this network is going to take in this history, all these previous design decisions, previous outcomes. It's going to spit out the next design decision. And what I want to do is, before I even start my experiment, I want to train this. And I want to train it using that model. And the thing here that's really important is the original objective I wanted only depended on that model. It actually didn't sort of individually depend on sort of design decisions. The sort of optimality of that, so the individual data, the overall optimality of that original problem was essentially completely stored in this model. And I'll sort of explain this a bit more carefully in a sec. But the key is that essentially the optimal neural network for making these decisions can be trained just from simulations from that model. So the objective only requires us to simulate from this model. So actually we can abstract all of this computation up front. And it's going to also, as Yusong asked about earlier, it's going to also turn out to get rid of our greedy problems as well when we do this. So to see why we can do this, let's look at the total information we gain from our experiment. So if we want the best overall experiment gives us the most information overall from all of the experiments. So we could say that what we want to optimize is the expectation of the sum of our expected information gain. So we've got a number of iterations, we get some information from each, and an expectation we want to maximize the sum of all of these information gains. And because sort of Bayes has this sort of works in this way, it's just going to be the same thing as the expectation in how much information I gain from the start to the end. So if I had this with sort of the one data term, then my second incremental AIG would have that posterior minus the next posterior, then that posterior minus the next posterior, and essentially I'm just going to get a telescopic sum where all of these intermediary things all cancel each other out. And so actually all I have to worry about is not what things looked at as I was going, just what was my posterior entropy at the end, what was my prior entropy, and then I can just look at the expectation of that under the data I'm going to generate. So where the policy network, this sort of deep neural network we're going to call a policy network, this is the thing that's sort of controlling the data generation along with the model, and we can just sort of train it to kind of work with this objective. And in particular, we can go back and we can use these variational bounds. So we can just take any of the variational bounds from before, and now they're going to look almost exactly the same. And what I'm going to do is, instead of training them with respect to designs, I now train them with respect to the parameters of this network. So I'm going to train my network so that it gives me the best decision making that therefore generates the best possible data. And again, the sort of joint optimization of this over our model parameters and over any sort of variational parameters I'm using will again recover back my sort of true total expected information gain and therefore the sort of optimal decision making. And because I'm now no longer being greedy, if I can sort of do this, if my network is kind of contains everything possible, if my variational approximation is universal, and everything happens to sort of be perfect, this will recover the true optimal decision maker that I could possibly had under the assumption of my original generative model.
But let's assume that this theta is no dimensional. If you're going for this for all possible parameters.
So usually it's not so much of an issue for theta to be low dimensional. It's if y gets very high dimensional at the moment is a bit of the problem. So there's different formulations we can use. So what's nice is that some of the variations, so this is actually not the bound we usually use. If we use this bound, it's problematic if theta is high dimensional.
Yes.
But usually we use the one with the marginal likelihood, where it's just an expectation over theta. So actually we don't have to model over theta. So the fact we've got these different bounds available becomes really powerful here, because we can deal with different high dimension. If everything's high dimensional, we're in trouble. Yeah. But if either the outputs are high dimensional or the parameters are high dimensional, we can deal with one way around by either using this sort of form or the sort of flipped form instead. I should say we're still currently doing this in quite low dimensions. So I'm probably not going to...
Because you have to make a decision how to do the next kind of experiment, which will, if theta is higher dimensional, then that you have a lot of space to cover. Have to.
Yeah, it's definitely true that at the moment we are not managing to do some kind of. We have some work at the moment that's potentially doing it much higher. So I've actually got a student where we've got a way of doing this as a diffusion model learning, and we're going to start hopefully to be doing it like we would do learning a diffusion model, which will suddenly hopefully scale everything quite substantially. We've done this to a few hundred dimensions, is kind of where we're at the moment. So I'm running a bit behind time, so I think I'll finish with just the example of this to kind of reinforce how this works, and then just sort of quickly kind of summarize at the end. So how this is going to end up training is we're going to start by drawing something from kind of our prior over what we're wanting to learn. So this is sort of a simulating a ground truth. So in the example, that's going to be the location of two sort of sources we're trying to find. So we're going to keep measuring the the strength of these sort of signals from these sources. We want to find where those sources are. So we've simulated the ground truth. We're going to first make a design decision. The first design decision is just an evaluation of the network with no inputs provided. And in this case, that will be a position to query that signal. We then use our model to simulate the actual outcome. So we've got in our model, we've got a design choice, we've got a true parameter, we'll simulate a possible outcome. Then we're just going to feed it back into the network. We've got a network that's carefully designed to take sort of varying length sequences. We'll now feed in this first data point we've got, pass it through, and get the next design. And then we just sort of follow this through until we've got all of our data. Then our loss is just evaluated as one of these sort of variational objectives on that set of data that we've observed. And we simply back-propagate this back through the system. We can now repeat this. We can sample a new theta. So here, a new set of sources, simulate a new set of data, can correspond to that new theta, and back-propagate. So over time, this policy network is going to kind of learn to make good data, until eventually you've got something that's sort of very adaptively making these decisions really effectively. And when we then come to the actual experiment, we no longer simulate from the model. We just sort of run an iteration of the experiment, pass things back through according to this. And then we're running a bit behind, but just one, I think, really important point I wanted to make with this is not only is this going to massively reduce your time, so these are real numbers from this problem. It went from about 2.5 hours down to 5 milliseconds actual runtime. It also gives you a huge performance improvement as well. So we did all of this to try and make things quick, but actually it turns out it massively improves state-of-the-art on the decision-making at the same time. And part of this is this greedy thing. It's this idea that we want to sort of be non-myopic in our decision-making. So if I've got a beam and I want to sort of split it evenly, if I kind of make my design decision in isolation greedily, I'll split it in the middle, and then I'll have to sort of split it to the side. But here, because we're doing everything completely end-to-end, we can learn that sort of better to do it in thirds. So there's this sort of non-myopicness to decision-making. And the other thing is that we've actually completely sidestepped inference. We never did any inference in any of this. We trained a network on purely simulated examples. We've back-propagated back to learn this network. And so we've actually removed all the kind of inference error. So a lot of the error that was actually occurring was that when we did the iterative thing, we had to get a new posterior. That new posterior was pretty approximate. And essentially, that sort of back-propagation, that then creates sort of the main sort of the error. If we remove that, we're never kind of actually doing the inference. And sort of more generally, as sort of a reasonably closing point, I think, for this, sometimes we can, with these new variational things, you can actually pretty accurately estimate these objectives on very big models. So if you take, say, some sort of Bayesian neural network, and I'll talk on Wednesday about why I think Bayesian neural networks, we never get anything like the posterior, and like we basically cannot do inference in them. We can accurately estimate the expected information gained in them, because we're never having to sort of work in the actual inference space. It's actually potentially easier because we're doing an optimization of this design. We don't have to cover the whole space. So it can actually be the case that sort of these things can work very effectively even in those scenarios. Where it breaks down is when we get lots and lots of decisions. So the more observations we make, the sort of more inaccurately that will stack up. And so the difficulty becomes how much can you sort of project into the future and how sort of non-myopic you can be. The real breakdown, it turns out, the pinch, if you say want to do sort of active learning with Bayesian neural networks, is actually the inference. You can actually make your decision making pretty much perfectly with these. And we've sort of done quite careful tests for that, much more than you can actually do actual inference. And that's because we only have to simulate one or, let's say, 10 steps ahead. We don't have to simulate and deal with all the data. We have a distribution. We have to simulate how that will change as we see a few new data points, which is in some ways actually an easier task than saying, I've got 1 million data points I've already seen, what should my distribution be given this sort of full set of millions. Okay, I think I'm sort of a bit out of time, so I should sort of get through. This is just a thing of saying we're trying to scale this up at the moment, the sort of stuff we're doing with things like DALI and stuff to really try and sort of start doing this at scale, making decisions working with people that work with sort of UK police forces for how we can kind of do police sketches kind of automatically for these things. We do things with sort of climate scientists. We were working on, but we've been scooped by some people in Singapore about doing this stuff for making ChatGPT ask questions rather than give you answers, and we're starting stuff in like sort of clinical trials and things as well. So to sort of recap, we've got this idea of using Bayesian experimental design. It's this sort of formalism of optimal decision making, and it really comes out very naturally from the information theory. We see that sort of Bayes becomes really inherent, and it's all based around this kind of model. We spoke about this use of adaptation. We can learn on the fly. We can take all that data on board, and we can utilize it to make subsequent decisions. And then I spoke about how there's sort of been a real big shift. There's been a huge change for these variational approaches in the sort of scalability and attractability. It's kind of completely game-changing of what you could kind of do without them to what you can now do with them. And similarly, these sort of policy-based approaches, again, have been a huge step forward in sort of actually the practicability of this approach. So I really think this is something that is now right for people to actually work on. I think it's an upcoming field that has sort of correctly been away because we've not been able to get around these issues, but it's sort of a much, much more practical thing that we've been doing previously. Very finally, I just want to say I'm hiring. So if you're interested in doing a postdoc, we've got a 2.5-year postdoc that can either be on this, active learning, or uncertainty and deep learning. So please come and chat with me if you think you might be interested in that. With that, thanks a lot for listening.
Okay, I think we have time for maybe one or two quick questions.
Sorry, I was close, you know. This was amazing, beautiful. Congratulations. This is really, really good. Two questions. Even if you can do experimental design, I think many data collecting, how data are collected will still be maybe be done before you get into the picture, or even if you do know what optimal decision to do, you end up getting something else. If you're drilling in the North Sea, you want to search for oil, it's actually very expensive to move the drill rig from one place to the other, and that is kind of a lot dominating cost. So it's beautiful, but how to make this more practical in the sense that this be put more into use?
Sure. So with like costs, that's not necessarily too difficult because you can.
Yeah, you can plug it in, but you know.
You can plug it in, but you can plug it in better than just sort of in a naive way, because you can say that 2 of these data points are worth 1 of these data points. Yeah. So you can actually, the cost literally goes in exactly, and it will still be in the right units. And you don't necessarily have some hyperparameters you're having to tune, because you can actually say you're hypothesizing that if I get 2 of these, it's the same as 1 of those, and so how does the cost change there? But yeah, I think there's a lot of challenges here to do it practically, and it's a very small field at the moment. There's really not many of us working on this, and I think that then gets reflected that a lot of the engineering and a lot of stuff is nothing like as developed as it is almost anywhere else we're used to working with. But I do think as we go forward, this is one of the main frontiers for machine learning in terms of it's a lot where a lot of things go wrong. I think a nice example of this is causality, how difficult it is in causality to sort of figure out once you've got the data what the causal relationship is. If you start controlling the process, you've got way more ability to sort of start making good calls. So it's difficult, but that's why we do research.
Yeah, you mentioned clinical trials. Can you ever get this through kind of a formal approval process in the end?
Yeah, so they've Bayesian adaptive trials were sort of actually put through like 2 years ago by the FDA in America. So there's a big shift towards this now being.
That took how many years?
A long time. It was well timed, I think. But there are definitely issues there, and that's not my area of expertise. I have collaborators that are, but I think, with working with people in those areas, I definitely think that there's a big future there.
I just wanted to mention, like, maybe you were also saying this, but this whole thing of like unrolling in the policy network stuff is really related to this dual. I mean, what we call this duality is kind of trying to not think about the last posterior parameter, but think about what actually got put into it. I don't know if you have any thoughts on that, or
so I think that's a good question. So I think what you're doing there is it's almost slightly the opposite way around with the same ideas, which is that historically you were doing it step by step, and our additivity is sort of already there because it's additivity and information, and you do it sort of like that. Now we're saying, well, actually let's jump to the end because these things all add up, they all cancel back, and for this scenario it's best to just go straight to the end and come back. We do have a paper under review that sort of goes between them as well, because the flip side of this is that at the moment, state of the art is a fully amortized approach, and that means so we've done the obvious thing, which is you basically now retrain the network as you go as well. So after 5 steps, you can retrain that policy network with the posterior you got so far. So there is a middle ground as well.
Yeah, what I was actually suggesting in the kind of things that we've been thinking about is that you can think of the final thing, but you can also think of what it's made up of. But actually it's a combination of the two that actually matters, because sometimes you make big jumps and other times you don't. The big jumps are what kind of are important, and your future experiments are somehow related to those big jumps that you made in the past. I mean, we call it like sensitivity in the end. We say things that have really made your final posterior what it is right now. It depends on the past experiments that were really informative in some sense. So I think maybe think about this.
Yeah, no, I think that's totally true. The optimality doesn't require any updating. So the original objective you could do, but practically, of course, not. And essentially what you're doing is you're regressing the whole space before you know what you're going to see. And then as you've seen some of your inputs, you want to re-regress your space based on the fact you've seen some of them. And as you say, there will be some jump points in that where your posterior contracts suddenly, and that means that suddenly you're looking at a much smaller area of your space. And what's unusual is your problem's not changed. Your objective has actually stayed as it was. It's just you're narrowing in where you're looking, and you can utilize the data you're getting to sort of basically refine your actual training, given everything was imperfect. To look at that. So yeah, I think I can't remember if we put it on archive if it's, yeah, but we have a paper doing this pretty directly.
Any other questions?
So in experimental design, so you're looking for a XI, so an experiment. But at the end of the day, so this XI parameterizes a posterior distribution, right?
I actually disagree with the first part. I don't think you are finding a design, I think you are finding a policy. And that's an important distinction, but the policy parameters will in some ways, it will influence, it doesn't parameterize your posterior because it's all stochastic. You still don't know what data is coming, so I would say, you could say it indexes a distribution over posterior as you might see.
But like, when you look at the definition of expected information gain, so it's a function of psi.
No. Well, okay, so let me answer that more nuancedly. Yes, but Chi is stochastic. So once you make it a policy, your design is not fixed. So your designs are random variables themselves. So you can't usefully index them because they're actually themselves just something stochastic. So if you I suppose it's not super obvious when you look at it like this, but this data generation is autoregressive. So I should make a choice and get some data and make another choice. So everything but the first choice depends on the data I've gathered, and is therefore already stochastic. So I can't really index because of the designs, because it's suboptimal to choose all those designs up front. I have to actually be adaptive. So the indexing is actually on the policy parameters, and then there's lots of distributions that can come out from that.
Yeah, so yeah, we're just thinking, so in the case of not in the greedy case of one step, so that this is the equivalent, right? So there is a lot of information in the posterior, actually, no? And so do you think because what you're trying to do is basically trying to not do the inference like you do posterior, right? When you do reinforcement learning or policies, etc.
Sorry, I didn't quite get the question, sorry.
So in this policy case, you're basically avoiding to do the inference on the posterior in the sequential case.
Yeah, I wouldn't use the word avoiding it. The policy shows you don't need the posterior. You're not avoiding something you could have done usefully. It simply doesn't require the posterior, or sort of more precisely the intermediary posteriors.
Yeah, but yeah. What I want to ask is, do you feel like maybe the posterior can give you like more precise information compared to not having the posterior?
So you could update your policy halfway through, but it doesn't actually change the optimum. So this objective, I can kind of have a policy that operates for the first 10 steps, say, and then a policy that operates from step 11 to 20, and the optimality of that is still dictated without needing the posterior, but knowing the posterior gives me a more refined area to train it to. I think we're being wrapped up. Just one very quick thing I want to say is we've just released a review paper for this, I've got to say, so if you want to learn more, have a look at the review paper.
Yeah, so we are a bit out of time, so maybe we can take the remaining questions offline. And let's thank Tom and Martin again for the great work.